One second. Okay, we are live in YouTube also.
Okay, so thank you, Pablo, and welcome everybody to the Foundations on Algorithmic Fairness. This is a workshop that several of the members of different ELLIS units, we decided to bring up together, and we found a set of speakers that agreed to participate in today's workshop, and also our second day for the workshop will be next Tuesday, also in the afternoon in Central European Time. We are being live streamed, so if you have questions and you are in the YouTube, type them in the chat, and we will do our best to address them. Otherwise, if you are here in the Zoom channel with us, simply type your question or raise your hand and we will give you your turn for questions. Our first speaker is Ricardo Silva. He is in UCL and the Alan Turing Institute. And as far as we can all see now, he will be talking today about prediction and action and inference. So thank you very much, and this online stage is yours.
Thank you very much for the introduction, Isabel. This is joint work with my colleagues Matt Kuzner, Chris Wesser, and Josh Loftus. So here we are going to make some points on the contrast between building fair predictors against building a fair policy, in which ways this can be approached on similar grounds with some concepts of causal inference. So it works with some examples that are mostly illustrative, they're not really full-fledged applications, that they mostly explain some concepts and provide some experiments on that, and hopefully open the floor for some discussion later on. So we have a prototypical problem where you may have a true label that you want to predict. And this y hat here is your predictor. So you like to y hat to get as close to y as possible using whatever information that you have. You can think of a choice or classify itself being a type of policy that decides how this y hat is going to be predicted. But you may have some protected attributes that you don't want to be using completely unconstrained definition of your predictor. But whatever this problem is, it doesn't change the way that true labels are generated. There is some sort of unfair process in the work in which, for example, many people from different backgrounds may get their job applications rejected. So your y there is a true prediction, is a true outcome of being rejected or not. Your prediction is not changing that per se. Maybe changing some sort of long-term effects in society, but as the moment you just create this predictor, the true label generating process is still taking place. So you may think that your goal here might actually to change the true model, the true process by which these labels are generated. So you should think here is not just creating a classifier, modifying a fair classifier, but actually change the way the word works. And previously, I have worked on prediction problems using this framework based on causal inference. So again, we have these diagrams here representing some sort of causal process. And there's a whole language behind that, which I don't have time to get into detail, but intuitively think of these arrows representing some causal relationship. So when you think about causes, you think about intervention. So you may think, hypothetically, what would happen if I controlled some of the variables in this system? So what I have here, for example, is the protect attribute represented as a square. Sorry, my screen is not updated. Okay, this protect attribute on the right, this has a square now is being controlled by someone. We imagine hypothetically that to control that. And there'll be changes propagated to the rest of the system, right? It'll be, this variable will be different depending on how I control that variable A, and this variable so on will also be suffering the consequences of a change in that protected attribute. So I may be interested in creating predictors y hat that would not change had a person belong to a different level of protected attribute. So I may be interested in building a y hat, for example, that doesn't depend on changes to A. So one way of doing that is, for instance, make my y hat to depend on some variables that are not on the causal pathway from A. And these variables could be hidden too. So I may be able to use information, for example, from variables which are affected by changes to the protect attribute, but only in terms of inferring information about variables which are not modified by the protected attribute. If I do something like this, I'm saying that my predictor doesn't change with hypothetical counterfactual values of the protected attribute. But as I mentioned to you, this whole past thing I described is just about building classifiers. It doesn't really tell you much about what happens in the real world. So you may be wanting here to create some action, some choice of action that changes the actual outcome. And you want to do this, but while being conscious about interactions with protected attributes. So here you say that the protected attribute has some particular impact on this outcome, but you may want to change this impact by controlling the relationship by some intervention that changes the way A and Y are related. So to give you an example, say you have a structure of the world like this, where you have here is socioeconomical status of the parents of an individual, and the place where this individual was born. And depending where you're born, you may attend different schools. So when you apply for a particular college, you may want to, in the school may want to predict what the first year average of that applicant would be. But they may use school quality as a predictor for that. And if you look at a diagram like this, you may think that place of birth, you may assume that place of birth is a protected attribute. You don't want to discriminate the applicants based on that. The problem, of course, of using school quality is that it is affected by the place of birth. And in this causal notion that it shouldn't be building predictors on attributes modified by the protect attributes, this would mean that I could not use school quality as a predictor variable. Okay, so here, for example, I'm creating a predictor that doesn't use anything that pathway from place of birth. So this, according to that notion, will be my counterfactually fair usage of the information that the applicant provides to me. So I would base my decisions on that prediction only, not on a predictor that uses school quality. However, you may think, okay, this still doesn't change the fact that your place of birth is affecting which school you go to. So ideally, as a policymaker, you may want to actually create a policy that changes the possible levels of quality of the schools that people in different places may attend. So the square here again is indicating a type of intervention that I would like to modify how this value comes to be. So I put these crosses here to indicate that this intervention could override the way by which school qualities happen to take place in the real world. And if this was the case, I could actually use school quality when creating my predictor of first year average for my college admissions process. So ideally, we'd like to have things like this, but of course, in practice, you may have only indirect ways of affecting. I may not be able to just magically declare, oh, this school now is going to be good. You can't really do that in practice. We have some other ways of indirectly creating a policy that may mitigate this relationship. And in principle, we are going to choose these types of policies, in this case, amount of investment, so that to minimize this impact. So this is this generic way by which you could represent policy making using these diagrams. And for what is worth, for the rest of the talk, I'm going to assume that my examples have this structure here, that you have just a direct relationship between my policy and the outcome, without any values in between the protect attribute and the outcome, just to make things simpler for the examples I'm going to discuss. Okay. So in having that in mind, one situation I'm particularly concerned with is when we have that your policies may kind of create relationships among everybody in a particular community, everybody in a particular domain. So you may have, for example, that for one particular individual, you may create some action that affects that individual's outcome, this individual number one. But if you think about individuals in the neighborhood of that person, it may be the case that the actions I choose for one individual may also affect outcomes for some other individual number two. Okay, we call this a spillover effect. So to give you an example of that, this comes from actual real-world studies on housing subsidies that may have, for example, that you're interested in improving people's income. Okay, so you may have, for example, the professional qualification is one possible factor influencing income. So you may have a policy that allows somebody to move to a different neighborhood with some better job opportunities. So there's maybe one action that one opportunity you give to that individual. But the problem is some other individual in the neighborhood may be affected because as people move, the quality of life in that particular neighborhood might decrease. So it's not only a win-win situation. If you give subsidies for somebody to move, somebody who's left behind might suffer from that. So this is a typical example of a spillover effect, that when you try to mitigate these relationships between A and Y, a particular person maybe affect what happens to another person too. Okay. So what is that you're trying to do here? Well, we consider this scenario where you may be able to give a treatment to a particular individual. So this could mean giving a subsidy or not. So this variable Z here means is binary. You do a treatment, give a subsidy, or you do nothing. So Z equals 0 means doing nothing. Z equals 1 means, for example, giving subsidy to an individual. So you may have an outcome which you think about reward. In this case, this reward would be the income in 5 years' time. So you want to allocate treatments to individuals under some particular budget. And this by itself would already include some interaction, some spillover effect, because if you give a treatment for one person, the other person might not get it. But you may want to quantify what's going to happen when it interacts with the protected attribute. It may be that a combination of a treatment and your social category, for example, among possible attributes, the combination of these things will have disparate impacts depending on what these values are. Some people, some particular background, you may think, oh, they're going to benefit more from the subsidy just because they're already in a group which has all sorts of other social advantages. So you may think somebody with a minority race, if you give them a subsidy, may still earn less than somebody else just because of some other difficulties this person might have while making use of that subsidy. So if you think about what maximizing this total reward across individuals, it's not only a matter of maximizing the total aggregate. We want to look at what happens to each individual and then realize, well, even though that particular individual will not add as much of a total reward to the pool of aggregated rewards, you don't want to disadvantage the person just because they belong to a particular social group A. Okay, so what happens here, for example, they may want to quantify a factor like this, which in this work we call counterfactual privilege, that given that you belong to a particular group A, little a, you may imagine that you will have a higher outcome if your group was modified to some other value A prime. So think about, even though I know already that belong to this group A, imagine what would happen if you had not belonged to this group A. How would be the difference in terms of reward to get because of that? So if you think this gap here, even though it adds up to the total reward, is not really fair because you don't have much control which group you belong to, maybe you don't want it to add up to the total reward just by capitalizing, just by making use of these gaps that are due to the factor A instead of other covariates X. So you don't want this to grow unbounded, even though they may provide a greater reward in total for that group of people that you have. So in principle, this idea that you should not just make do of increasing of reward that are due to belonging to some particular group. It means that you don't want to ignore that while maximizing your while maximizing the outcome of your policy. You want to bound all these total contributions to the reward while you do your allocation of treatment Z. Okay, so what does it boil down to in this case? Well, we can have this integer program problem where, again, for each of the individuals, you're adding up their reward. So here you're adding up for everybody this expected reward, but not only you have the budget constraint that you have only as many possible subsidies you can give, but also you're controlling the contribution of the protect attribute to the rewards. So you're not allocating particular subsidy to someone just because it increases the total reward that is due to the factor A. You take into account that you don't want just to construct your policy in this greedy way, just for the total aggregate amount, but also respecting that this so-called counterfactor privilege is going to be bounded for each individual. Okay, so this contribution of A cannot go arbitrarily adding up reward the total pool. So sometimes this may not be feasible. It might not be feasible because there's already so much disparity in the population, right? There is no policy that can satisfy that solution. But then this is the case is because your actions that really cannot do much. So this is not really part of the problem. It is not a problem with the problem formulation itself. It may be the case that your policy just cannot find any feasible solution. If you can find a feasible solution, then you can find it via this integer programming problem. Okay, well, let's give an example on that quickly to wrap this up. So this is a synthetic example because it's based on assuming that a particular data generating process represents the right causal relationships in the world. So what I'm going to do here is generate some synthetic examples based on real data. This real data comes from schools in New York City with all these values that we have here, including the protect attribute, which is race. But we have other attributes that contribute to having a good percentage of students taking college admission exams. Okay, so Y here means a percentage in a particular school taking a college admission exam, in this case, the so-called SAT. Okay, so this protect attribute is per school. Is a real number between 0 and 1, indicating the proportion of people of minority and race, in this case, non-white. Okay, so this is a postulated diagram showing relationships between protect attributes and outcome Y. My intervention Z here is providing advanced calculus course in that school. So you think of this as maybe as an extra nudge that incentivize more students in a particular school to take that college admission exam. Okay, so that's my intervention. I'm incentivizing on providing calculus courses in that particular school. And this may have a spillover effect because at least in New York City, you're allowed to take courses in schools which are nearby to you. So you may have, if you're a student in a different school which does not have that calculus course, you may still be able to take it because it's provided in a school nearby to you. So that's where the spillover effect comes across schools. It's just due to geography, just being proximity between schools. Okay. So if this model and the data fit a causal model generates synthetic data to be able to evaluate effects of different policies without getting details, we just fit a linear model based on this real data and generate simulated data to evaluate what these different policies might entail. So the details here don't matter that much, but essentially providing a way of assessing the expected rewards as I vary Z, as I vary my policy. Okay. And what we have here in this axis is that constraint tau that I mentioned to you. The larger it is, the more I ignore the contribution that is provided by the protect attribute. So here, you're going to see what happens if I don't put any constraints in my model. Just maximize my policy to maximize the total number of students taking the SAT examination. And the colors indicate the distribution of the majority race in each school. So you can see when I don't have any constraints, most schools who get access to this calculus course are actually schools that are majority white. Okay, as I constrain my solution, I do get a reduced reward. I can show there is a kind of trade-off there, but I also increase the diversity of the majority race among the schools which get that treatment. So there's a trade-off here because it's not only about maximizing the number of students, but also allowing more diversity on the majority race among them. So here's actually showing you the objective value. So it varies from 35% to 37% of kids taking the SAT, where 35 is I get when I really constrain to be more diverse, and 37 is what I get when I don't put any constraints. In essentially, everything flips towards schools with majority white students. And this is not the only criteria should be right. So this constraint tau controls this trade-off between getting higher expected rewards and mitigating the influence of factors such as race on the total reward that you're obtaining. Okay, this is just here showing geographically what happens. Again, the same information. Here on the right is unconstrained. On the left here is if it's a more constrained control on the contribution of the majority race among schools to the total reward. And see the colors indicate again the majority race, and then this is just a geographical, just a spatial way of showing how diversity increases if I have this extra constraints put in my resource allocation problem. So as I said, ultimately, it's not just about prediction like some test work I've done myself. You want not only to change a classifier, you want also to change how the reward labels are generated. And for that, you have to think in terms of problems of intervention, which essentially boils down to having some assumptions about the causal influences of your actions. All right. So if I switch work, we want to include some uncertainty or estimates, which is not something we do here. We assume the model is given just because it's an optimization problem, but the model splits data. So we wanted to report the uncertainty on the estimates of the reward. And because this relies on some causal assumptions, we also wanted to consider how the conclusions would change under some changes on your assumptions too. Okay. So this is all I wanted to mention here. I'm very happy to take some questions for now.
Thank you very much, Ricardo. Very nice talk. So let's see if we have any question in the audience. Maybe if you have questions, please raise your hand by using the feature of Zoom, or type them in any of the chats. So while maybe people become a bit less shy, I can maybe start with a couple of questions. So basically, you saw this trade-off between diversity and reward. Mm-hmm. But my question in this example is whether this reward is measured over an objective measure of actual quality, or whether there is, I mean, where is the source of this trade-off and how important it is, or how it can vary depending on the problem.
Right. So to give this, to be based on this example that I mentioned here, and I'm not a social scientist, I'm just making this as an example for a method. So don't take my word here as the word of somebody who actually is an expert on this domain. So the idea here is the reward, of course, is completely problem dependent. It's up to the social scientist, up to whatever the policymaker who thinks this is a good measure that you want to maximize. So it's really problem dependent. You may think that, well, this is at least one step towards having access to higher education, right? Taking the SAT, taking this college admission exam is one step towards college acceptance. So you may think of this is tangible, let's go with it, it seems reasonable. And you may think that this is disparity for a variety of reasons, which here is just wild conjecture, it's just for illustration. You may think, for example, that students from a minority, for all sorts of reasons, have less confidence. So when you provide the opportunity to take these calculus courses, there will be an impact, but the impact will be smaller than the impact on students who come from a white background or a school with majority white students. So you may think I have just one allocation to make, for example. And if you make this allocation to a school with minority, where the majority of the students comes from minority group, there'll be a smaller bump in terms of the total reward. But you may think this is fair anyway, because you think the protect attribute tells you that you should discount the fact that you just don't have, let's say, full agency on what you're doing because of all sorts of conditions you're exposed to. So that's where the trade-off comes from.
I see. Thank you. I think there is another question by Asia Viega. Maybe you can unmute yourself. I think it should be possible now.
Yeah, sure. Thank you. Thanks, Ricardo, for the great talk. I have a question about something you mentioned early in your talk, that it might be possible to break the causal relationships between different variables by policy changes. And my understanding is that in causal modeling, lots of the results or lots of the conclusions depend a lot on the assumptions we make about the structure of the model and the dependencies between different variables. I guess the question, and very broad and high level, is what would be the form of evidence, and how concrete this evidence would have to be to then go to policymakers and say, look, we really think you have to make a policy change to break this dependence between these two different factors.
Mm-hmm. Yeah, so here, this data is observational. So in one sense, there was no clear, no known mechanism by which this past data, the allocation of calculus courses was done. So it's observation in the sense that this wasn't a randomized trial. The data that he had, he wasn't a randomized trial. So can you use past observational data to make claims about what will happen under a particular policy if you can justify things such as, I know the sources of confounding. I know why this action was taken in the past, given some covariates. And there's already a literature on that. I'm not saying it's easy, but what I'm saying is you can tap into that literature to understand, for example, that even though it was a randomized trial, there's some basis to be able to say, well, under a policy, this is what would happen. And then that's how you express that's how you express your assumptions that this will translate into a policy, by tapping into this literature and observation studies.
Mm-hmm. Right, makes sense. Thanks.
Thank you very much, Ricardo. So I think we don't have any more questions, and we are exactly right on time. So maybe we can thank you very much again, and let's move to our next speaker, Stefan Grunenwald. So I cannot find you.
Okay.
Hi. So maybe you can try to share your screen. Stefan is at the University of Lancaster. Yeah, we can. And he will be talking about how kernel methods can help us to build up algorithmic fairness. Thank you.
Thank you. So I think this talk from Ricardo was quite useful as a warm-up to my talk. So I think his A in my notation is S. And instead of being interested in modifying Y, I'm here interested in modifying the features X. So essentially I've split it here into S and X. S are sensitive features, very much like in Ricardo's talk: age, gender, country of birth. In UK last year, we had this problem with state versus public schools for grading, so that might potentially also be a sensitive feature. And non-sensitive features are pretty much everything else that you might care about for prediction, for regression, for grading, for selecting a candidate for a job. So the key problem I'm kind of interested in here is that generally the variables that we care about, X and S, are dependent typically. So it's not sufficient in simply ignoring the sensitive features and just working with X, because X, yeah, I think that's pretty much similar to Ricardo's talk. X often is influenced by S. So kind of the very simplistic problems that we were looking at here in this work. By the way, I've put pointers at the bottom, so we have an archive link there and a GitHub if you want to use some software. So the very simplistic problem we were looking at here is a way to replace the feature X with some new feature Z, which is in some way close to X. So the idea is here to preserve as much information as you can, but ideally is independent of the sensitive features. I should possibly also say the talk is a bit more on the technical side. If there's any questions, I don't mind if you ask in between, if there's anything unclear. Okay, so let's start with the setting. So the first thing is I want to define an optimization problem. So ideally, I want something which I can formulate in terms of vector spaces. My key constraint is independence between Z and S. So the first thing I'm kind of aiming for is a vector space description of independence. I've scribbled this down here on the bottom. So the typical description for these kind of things is to check if the expectation factors into two parts. So if a product between h of z times g of s, h and g being here continuous functions that act on our features. So h is applied to the feature z, the ones that we want to be independent of s, and g is applied to s. So if the expectation here factors into a product for all continuous h and g, then z and s are independent. So h and g take here the role of test functions that test for dependencies between your random variables. So that is, in a way, a description in form of a vector space. The difficulty with this description is that you have to test for all continuous h and g, which are obviously a lot. So while this is a nice description, it's not necessarily particularly practical. So in the next few slides, I'm trying to reduce that to something easier. Essentially, I will relax this assumption somewhat to get a nice linear constraint that can easily be dealt with. First steps that I'm doing is we're moving here to a subspace of the continuous functions, ideally a subspace that allows us to approximate any continuous functions well. So that subspace for me will be called H throughout and will be a reproducing kernel Hilbert space. I explain later why the reproducing property is useful. Using that, we don't lose anything. Z is still independent of S if this expectation can be written as a product for all continuous G and all H in the ArcHS H. I should possibly also mention here quickly, this is very closely related to the MMT criterion, if you're aware of that, for testing dependencies between random variables. Okay, so until now, we didn't really gain that much yet. We still have to go over two big classes of functions. So we're now trying to simplify this problem. So first thing, you don't need to know much here about ArcHSs. The only thing that I'm really using is the reproducing property, which for convenience, I've scribbled down on the top. Reproducing property is saying there's some map phi, which maps from our space X, where our non-sensitive features attain values, into the reproducing kernel Hilbert space, and it lets me write point evaluation h of x as an inner product between h and phi of x. Given that our description is z is independent of s, if the expectation again can be written as a product, main difference now is I've written this as an inner product between h and phi of z instead of h of z. Important is here that is really the key difficulty in this whole approach. Phi is generally a nonlinear function from the space where the covariates attain, sorry, where the features, non-sensitive features attain values into the reproducing kernel Hilbert space. And usually it's a quite, has no particularly nice shape. So it's really not a great function to optimize over. So the question is now, there's nonlinear constraints that we have in that. How can we simplify that? How can we get something still meaningful, but easier to deal with? So the key step here in our paper is to do the following. We ditch this route through the space X, where our non-sensitive features attain values. and then using phi to get into H, but we allow directly a random variable to attain values in H itself. So we are working here with vector valued random variables that attains values in H. And the constraint we now care about is inner product H and Z, if we take the expectation over Z, times G of S we should be able to write this as a product of expectations for all H in our RHS and all continuous G. Important here is this is a linear constraint in Z now, simply because inner products are bilinear multiplications, don't change that, and expectations are linear. So now we moved from a nonlinear constraint, because we had this phi involved, to a linear constraint in Z. And Z is the variable we are interested in finding. If you like diagrams, this would be the easy description. We somewhere have our sample space or probability space omega. We have our non-sensitive features X, which attain values in some space. We have our sensitive features, which attain values in another space. These are really only coupled through omega. I've discussed already the reproducing property. So using X, we can get to this space blackboard X, and then with phi, we get into the RHS. And our approach ditches this route now and goes directly from omega into H. We're looking directly for Z, which maps into the reproducing kernel Hilbert space without going through X, without using phi. And that allows us to get to a linear constraint, which is easier to deal with. So our new goal, so if you remember like 2 minutes ago, when I introduced the problem, our goal was independence and approximate the original non-sensitive features as well as possible. So I modified this goal now somewhat, weakened it. It's a relaxation. It's not as strong as full independence. So our new goal is to find a vector valued random variable Z, which fulfills this constraints that I've discussed now in the last few slides. And Z is in some way close to X. By that I mean that Z minus phi of X has the smallest distance. So this is here an L2 norm. Details are not too important. But this here is an L2 norm between the random variable Z and the random variable phi of X. And this 2 norm should be the smallest among all 2 norms that you can achieve with any Z prime that fulfills our constraint. So it should have the smallest distance to our original features after being mapped to the RHS while fulfilling the constraint. So these are now our new features that we aim for. For kernel methods, this is completely sufficient. If you have the Z, you can directly work with your SVMs with anything that uses kernels. That works perfectly fine. So this is quite a nice feature, reduces dependencies, but doesn't give us full independence. So it's a relaxation of full independence. Okay, let me talk like very quickly about the solution to this optimization problem. You might recognize this here as an L2 projection onto a linear subspace. So star is a linear constraint. So it describes a linear subspace within our Hilbert space. And this one here is saying we're looking for the closest point within this linear subspace to phi of X. So what we're dealing with here is an L2 projection. We are trying to find a projection in L2 space in a linear subspace defined by our constraints. So you might, I don't know, if you're a bit into probability, you might recall that there's close relations between L2 projections and conditional expectations. Conditional expectations are essentially projections. So our solution is using a conditional expectation of phi of X conditioned with respect to our sensitive features. So I don't want to go too much into details here. So for people who know it, this is a Kolmogorov conditional expectation. So this is a random variable attaining values in our Hilbert space H. You can also, if you like, write this conditional expectation as a function of your sensitive features. So as your sensitive random variable changes, this conditional expectation attains different values in your Hilbert space. So the new features that we have, so our new Z that we will use is now phi of X minus the conditional expectation of phi of X given S plus some normalizing factor E of phi of X, which is not too important for the understanding. The idea is here essentially that we subtract of phi of X the best regression or prediction of phi of X given S. So we essentially cancel the mean effect of S onto phi of X. So there will be still other effects in the data, but we cancel here the mean effects that the sensitive feature has onto the non-sensitive features. And this is more than in the linear case, because phi of x here is nonlinear. Everything happens in the RHS. So we get something stronger than simply doing normal decorrelation, if you like, in your linear feature space. Possibly also worth mentioning, if S and X are already independent from the start, then you regain your original feature. So that will be simply phi of x. So we only change your observations if there are dependencies between your random variables. So just a very simple proposition that is not too difficult to show using properties from conditional expectations. So the set that I've just shown to you fulfills the constraint. So it fulfills this kind of weaker independence constraint, and it is the best approximation of our original features, or better, of phi of x. So it gives us the smallest L2 norm with respect to phi of x among all random variables that fulfill the constraint. So we, in some way, preserve the most information that we can, given the constraints that we enforced. The only thing that you can improve here really is possibly strengthening the constraint to get full independence. Okay, let me give you a quick example just to have a nice plot and give a bit of an idea of what's going on here. Let's focus on the top two plots for a second. Actually, my notation here is, again, very similar to Ricardo's. I used here U, I guess, for another random variable that influences the non-sensitive features. So we have here the non-sensitive feature is a linear combination of sensitive features plus U. S and U are independent of each other, and U in this case was, I think, simply a uniformly distributed random variable. Now what I'm plotting here is the function h1, which is simply taking x to the power of 2. So simply the quadratic function. You can imagine here this being a regression function that you might infer, and you don't want your regression function to have strong dependence on the sensitive features. So let's look at the left side first now. What I've plotted here is on the x-axis, we have S, the sensitive feature. On the y-axis, I have the prediction h1 of x. You might predict some kind of values that you're interested in, some y that you're interested in. What you can see here is there's obviously a significant dependence between S and h1 of x. These two random variables, our prediction and S, are extremely dependent. So the red curve that I've plotted here is the best prediction of S for h1 of x. So it's essentially this conditional expectations that I was talking about. Now on the right side, you see our prediction h1 using our new feature Z, again plotted against S. And what you can see now is obviously the dependence between these features is strongly reduced. It's not fully gone, so there's in the variance in particular still some relation between the variables, but the systematic trends that you have between S and h1 of x disappeared. So this part is gone. The bottom figure is pretty much the same. I'm using here the sign instead of x squared, and you see it's the same kind of relation, S versus h2 of x, strongly dependent. If you look at S versus the new prediction, h2 and z, there's hardly any relation between the sensitive features and the predictions that you can observe. A key point here that I should possibly point out, the feature Z doesn't rely on which function h1 or h2 you are using. So we construct Z once without any kind of function in mind. You need the RHS, yes, but otherwise we don't have any particular function in mind. And whatever function you will gain from your regressor, this kind of transformation will apply. So you don't need the function first to transform, but it will automatically do this transformation for you. So we calculate Z once, and that whatever function you get out of your regressor, you will get curves like on the right side. So that's quite a neat feature of this thing, that we don't need to know what kind of regression function you're calculating, or you don't need to have some kind of joint optimization where you find your regressor and then try to remove dependencies. So you do this upfront once, then apply your regression function. Okay, I think I have 10 minutes roughly. So there's quite a bit in the paper, you can have a look at it. So, but I wanted to kind of just pick out one of the topics that we're dealing with here. So I think one that is quite interesting, a bit more theoretical, is what can we say about the dependencies between these new features Z and S? So first off, I can point out that the nonlinear regressors are always decorrelated with any function g of s. That is an easy first observation, but potentially we can say a bit more about the dependencies between z and s. So in the next few slides, I'll give you a bit of an idea of what can be done in that context. So first thing, I'm back to my constraint, and I'm just saying here that this constraint is stronger than the usual decorrelation. So we can say a bit more about the dependencies between z and s. So first indications that this is a bit more than decorrelation is the following observation. If z is equal to phi of w, so phi being our map from the non-sensitive feature space into h, and w being any random variable, I don't care what kind of random variable that is, but if z can be written as some phi of w, and h is big enough to spot any kind of dependencies, so in kernel speaks, that would be a characteristic kernel, or often a universal kernel is sufficient. Since the constraint I've given you actually implies full independence between z and s. So if z lies in the range of phi of our feature map, then we will automatically enforce full independence. So generally, I should say z unfortunately will not lie in the range of phi. But then the question is, what happens if z attains values close to the range of phi? So I will call this a manifold. It's a usually low-dimensional manifold in our Hilbert space. So what if z lies close to this manifold induced by phi? Can we say something about the dependence between z and s? So key in that thing is how far z will lie away from this manifold. So I need a bit of notation here. I will throughout call phi of x, so the range of x, so the range of, the range of phi. I will call this m. And it is important to understand how far z is away from this manifold. For that, I need some kind of distance measure, which I call here the distance between z and m, which is essentially just checking in the Hilbert space and in expectation, how far is z away from the manifold. I should say there's under quite mild conditions a w such that the distance between z and m equals the distance between z and phi w. So I can find a new random variable which essentially picks the closest points on the manifold to z, and the distance between the manifold and z is simply the L2 distance between z and phi of w. So in the following 3-4 slides, I will move to this projection of z onto the manifold. I can give a bit more intuition later on if anyone has some detailed questions. And now I'm interested in characterizing the dependence between w and s. So I can also move later on to dependencies between z and s, but w is easier to deal with. So if you look in our paper, we have a statement about the relation between w and s, and z and s, the relation between w and s is much easier. So if you want to quantify dependencies, you need to kind of find a way to express this numerically. Typical way for that is to measure the difference between intersections of events, one relating to w, so in this case, our non-sensitive or new feature, one relating to our sensitive features. In this case, A relates to W, B relates to S, and you'd like to find an upper bound on the difference between these two things. So if these absolute values are equal to 0, then the two random variables are independent, and the higher this value gets, the more dependency random variables are. So you're looking into finding small bounds for the difference between these two expressions. And I just want to very quickly give you a bound that we have that depends on the distance between z and the manifold for the dependence. So the key quantity, so I'll kind of unpack this now in the next 2-3 slides. The key quantity of this bound is this function psi of A. A is some event relating to W, so we measure some kind of property of W. And what this is saying is it contains here 2 parts. The first part measures how well our RKHS is able to approximate indicator functions relating to W. So you can think of, if you like, of a step function that relates to a particular event about W. Something happens about W that we want to quantify. And now we are interested in how well can age approximate that indicator function. So the first term in psi essentially measures how well you can approximate these indicator functions. The second term that I've scribbled down here has the norm of age and some quantity, which is the distance between Z and the manifold. So you can think of that as a regularization or penalty term. So what we're trying here in some ways, we're trying to approximate indicators as well as we can with our RKHS, but we can do this only to some extent because the higher the norm of our function h is, the more we pay in the penalty. So we have here a trade-off. One thing that you can, by the way, observe instantly, if Z actually attains values on n, then the penalty disappears. So the penalty only kicks in if we have some distance between Z and the manifold. Okay, so the statement I wanted to make is, you can possibly forget the first two lines. The statement I want to make is the bottom. So the difference between the intersection of A and B, probability for Z, and the product is upper bounded by this psi of A prime. And the psi of A prime crucially depends on the distance between the manifold and Z. So just like a small figure to make this a bit more intuitive, we have somewhere here an RKHS H. I've carved out here two dimensions given by the vectors E1 and E2. Blue here corresponds to my manifold, so that would be the image of our feature map. And gray would be just visually a region in which Z can attain values, and we will have a low dependence between the resulting random variables Z and S and W and S. So if Z lies close to the manifold, then the dependence between our new features and our sensitive features will be small. If Z lies far away, then this bound is pretty useless. Okay, how many minutes do I have left? 2 minutes or 5?
Yeah, you can use 2 to 3 minutes.
2 to 3 minutes, okay. So let me very quickly give you just now more to the practical side. How do you use these things in practice? So first off, I didn't mention that I have to estimate these conditional expectations. We have a plug-in approach for that. You can have a look into the paper. Also in GitHub, we're using that. We have an analysis of the rates of convergence. I don't think this is here of key importance, but if you care about these things, have a look at the paper. Generally, the approach now works in the following way. Say you have 2 n data points, like that is one particular way to deal with it. Split the data in half, use half to estimate the conditional expectations, and the other half to generate your new features. Zi, which I've scribbled down here. En here means the estimate of your conditional expectation. Given these estimates, we can calculate something which we called the oblivious kernel matrix. So it is essentially replacing your standard kernel matrix in kernel methods. So what this is saying is you simply take the norm of your Zi's on the main diagonal and the inner products between Zi and Zij on the off diagonal. So this is very similar to what you would see in a normal kernel matrix. Instead of kxi, you simply have here the inner product between Zi and Zij. The matrix is positive definite, and essentially you simply use that matrix instead of your kernel matrix when you run an SVM, a ridge regression, whatever you want to do. You can simply plug it in and use your standard kernel method with it. Computational complexity of this thing is also not too bad. So we have a simple algorithm which calculates the oblivious matrix for you in O(n) squared operations. So you have an O(n) squared upfront time cost to get this matrix, and afterwards it's just the usual kernel machine without pretty much any difference. But the features you have now fulfill this weak independence constraints that I talked about, and try to approximate your non-sensitive features as well as possible. Just on one slide, so we have in the paper also experiments where you can look at. I didn't paste any in here in the talks, but just how you would use these things in a very simple setting. Say we go for a ridge regression problem. We want to predict y from x, but have some kind of independence of s. So we want to use these new features z. So the regularized optimization problem, I've scribbled down here, h hat would be essentially your standard ridge regression solution. Just you should observe here, instead of having here h of x, you have now, here's the inner product between h and zi. So our predictors generally attain the form of inner product h between zi instead of being an evaluation of a function. And if you do that, you can verify that it's quite easy. You get the standard solutions that you get in a rich regressor. So h hat would be a weighted combination of your new feature zi. Alpha as a weight vector would now be the oblivious matrix plus your regularization term applied to your labels. And I think that's just my final slide. So this new independence conditions that I've talked about, there's still a bit something mysterious about it. So I think there's still some scope for getting a better understanding of how much that reduces dependencies and what it does to your features. There's also the question if this feature set can be improved further to get full independence. In particular, this distance between the manifold and Z matters a lot. So potentially there might be a more clever way to exploit this distance and find something that reduces dependencies further. Finally, I didn't really talk about how the interaction between these Zs and the, for instance, kernel machines that you use in SVM afterwards go together. There's obviously some element of estimation error coming in because I generate these ZIs using data, estimating a conditional expectation, and there's an estimation error from, for instance, the SVM. So how these things go together, we didn't explore this, but this is obviously a question that is useful to study. Finally, what I was using here is a key tool versus vector valued conditional expectations. I'm sure there's other uses of these. So just as a final question, I wanted to mention that. And I think that's it. Thank you.
Thank you very much. I think we have time for a very quick question. Evgeny?
Yeah, so I think thanks Stephen for a talk. So you have a bound there on the independence, which is quantified via psi. But this psi is, yeah, right there. But this psi is also a function of the Hilbert space, right, that you use. So would it be...
You mean it's influenced by the Hilbert space?
Yeah.
So yes, it depends.
Would it make sense to choose the Hilbert space properly? So maybe the first part is 0, or maybe at least theoretically there exists such Hilbert space.
Yeah, so typically if you have a universal Hilbert space, for instance, you can approximate each of these psi a primes, depending on how your measure is, but you will potentially need a quite high norm. So yes, there is some dependence on the kernel here, depending on what events you potentially can describe well and what you can't describe that well. I tried to look a bit into it of how well this approximation works for particular cases, but that's actually not such an easy problem to characterize. So yes, there is an impact of the kernel onto which events you can approximate well, but I don't think it's a very simple relation between the two.
How do you choose the kernel in practice in your experiments?
I guess like in every other kernel method. So I would definitely go for something like a characteristic or universal kernel just to be sure that you can characterize your dependencies well. But otherwise, I don't think there's anything that is really guiding your kernel choice here.
Thanks.
Okay, so I think we can move on to the next speaker. Thank you very much, Stephen, for such a very nice and technical talk.
Yes.
So, Asia, I guess you were here somewhere?
I am, yes.
Hi.
Hi.
So maybe while you share your screen, I introduce you and then you start. So our next speaker is Asia Viega. She's at the MPI for Security and Privacy in Bochum. Not sure whether physically she's right now there, but eventually I guess she will.
Last week, yes, physically here.
Okay. And she will be talking about data minimization and fairness. Thank you, Asia.
Thanks, Isabel. Thanks for having me. My name is Asia Viega, and I'm now a tenure track faculty at MPISP. I'm leading the Responsible Computing Group. And today I will tell you about the GDPR requirement of data minimization and how implementing this requirement in profiling, personalization, decision-making, and other socio-technical machine learning systems leads to some interesting questions at the interplay between this principle and fairness. I do a lot of the work around data minimization in collaboration with my colleague, Michelle Fink, who is a legal scholar at the MPI for Innovation and Competition. But a small disclaimer here is that this talk is going to focus on the computational rather than legal perspectives on this. So let me start with the definition of the data minimization principle. So the data minimization principle in Article 5 of GDPR is defined as follows. Personal data shall be adequate, relevant, and limited to what is necessary in relation to the purposes for which they are processed. And there is a lot to unpack here. This is what I'm going to do throughout the talk, focusing mostly on the limitation and on the purpose. And purpose here is guided by another principle that is called purpose limitation. And I won't be going into the detail of talking about this principle. So for now, it's enough to say that one of the aims of the principle is to limit the amount of data that we collect. There are other goals as well, but this is one of the main ones. And there has been a lot of discussion about this principle recently. And some of the sources of this discussion are is this disagreement between different camps who think data minimization is desirable and some camps that think that it just has too many undesirable consequences. So why would we want to minimize data in the first place? There are lots of different reasons to do it. I guess the first one is that if we're not collecting data that we do not need for a specific computational purpose, we're just avoiding the unnecessary risks that come with collection and storage of some data. And these risks can be related to unintentional disclosures or hacking of the infrastructure of the provider that is collecting this data. We are possibly limiting and preventing inference of personal information that is not explicitly there in the data. So for instance, I might be collecting product ratings, and these product ratings would enable, if collected in large quantities, would enable, for example, to predict people's sexual orientation. We can further increase user control over the data, their agency, and general understanding of what is going on and what is happening, what does the service provider know about me. So it's an important component of giving users this sort of power. And finally, more on a societal level, we're limiting the potential for surveillance and targeting. And there are many more other reasons why we might want to minimize data. But there have also been voices that said data minimization has many undesirable consequences. One of the reasons that have been mentioned is that if we don't collect data, this is going to curb innovation. Lots of the progress in technology we've seen over the past couple of years, exactly because we were able to observe lots of interaction data about how people use different platforms and what they do. Among these potential desirable uses of tech are socially desirable technical innovations. For instance, if we're collecting lots of search queries, we might be able to use those queries to predict disease outbreaks. And on a more higher level, if we don't collect as much data, we might limit the competitiveness of the European economy as compared to the competitiveness of companies that operate or are based out of different markets. And finally, one of the big arguments against data minimization or reasons why people think it can be implemented is just that it's just impossible in the world of big data, right? Machine learning models need a lot of data, so there's just nothing we can do. And for me, as a computer scientist, there are two questions that immediately pop up here when I see these arguments. So the first thing I pay attention to are these impossibility arguments. So is it really the case that we cannot do anything if we have machine learning models that need a lot of data? And the second thing, like how harsh is this trade-off? Perhaps not all of the data that we're collecting is actually necessary. And these reactions stem from lots of different empirical observations that have been made in the literature in actually a number of different fields within computer science. For instance, in 2008, in this paper by Krause and Horwitz, what they observed is that in personalized search, when we collect more and more user features, the utility or the quality of personalized search decreases. So it seems at some point we can just stop collecting user data, and we're just going to get just as good utility from the service. And this is not the only example. So similar examples have been observed in the context of deep learning models, in applications in NLP and computer vision. So there is lots and lots of empirical evidence of this kind. Like, you know, that the quality of the system it flattens essentially at some point as we're collecting more data. So there's some empirical evidence that suggests that actually we could do better when it comes to data minimization. But there's also other evidence in terms of computational techniques. So there are lots of computational techniques that in fact can be seen as data minimization techniques. Those include techniques like feature selection, where we remove certain features from the data before we train a machine learning model. Outlier detection, where we remove noisy data before we train models. Or active learning, where we selectively label data that we feed to machine learning models as we feed them. So definitely these techniques look promising, but they are mostly applied in cases where we want to limit the cost of annotations or the accuracy of the models, and not necessarily to comply with the legal requirement of data minimization. So there's empirical evidence that we could do better in terms of data minimization, and there are computational techniques that could definitely be adapted to do this. So what is the reason this principle has not been adopted more widely so far? When we looked into this, we noticed two main reasons. So the first reason is that there is a scarcity of guidelines in general. So there is a paper that was published at SUPS in 2018 that looked into how software developers understand data minimization. And essentially what they found is that people understand this principle very differently, and there is no unified guideline of how this can be implemented. And second, we lack operational definitions of this principle. We looked at some of the guidelines issued by different data protection authorities, and we noticed that they generally either don't talk about data-driven systems, or they only mention very high-level techniques without detailed guidelines on how to actually implement them. So that brings me back to the definition of data minimization. And inspired by the lack of these guidelines and operational definitions, the question we've been asking ourselves, how do we actually operationalize this definition in the context of data-driven systems? What does it mean to limit the data, and what is the purpose of data collection in systems like this? So when thinking about systems such as personalization, profiling, decision-making, one observation that we can immediately make is that very often when we are collecting data, we don't do this to actually offer the service. We collect the data to improve the service, right? So I can offer people random recommendations. I don't need to know anything about them to give them some recommendations. The reason I'm collecting their past product ratings is because I want to improve the service. And so this insight led us to the interpretation of the purpose in the context of these data-driven systems. So our proposal is that we should tie the processing purpose to improvements in very specific performance metrics. Once we have the purpose, we have to figure out what does it mean to limit the data in relation to that purpose. And essentially, in our work so far, we have experimented with two different definitions, and these are definitely in final, so other definitions are possible. The first definition essentially says that we should minimize the number of data we're collecting from each user. Say you're collecting K items from each of the users, such as search queries or product ratings. And we want to do this in a way that minimizes the global loss in terms of the system performance. So this is a global data minimization principle. We can also look at this per user. So we might say we want to minimize the amount of data we're collecting from each user, such that also for each of the users, the loss in the quality is bound by limited by a certain threshold. So our goal in some of this previous work was to understand what would happen if we actually implement data minimization according to these principles. So just to very briefly give you an overview of the setups in which we experimented with this, we experimented with recommender systems. And so we had a background recommender system that was sort of our system that was trained using some background data that the system might have available from different sources. And then we have a set of minimizing users. And each of these minimizing users has an observational pool from which an algorithm can observe data. And we have some test data that we set aside to see how well we can minimize and predict. Some of this observational data is selected by a minimization strategy to show to the recommender system, and some of it is minimized out. And so the first question we were interested in is just seeing like what's going to happen if we limit the amount of data we're collecting from each user. So what I'm plotting here on the x-axis is just the user ID when we order the user by the users by the error incurred by different minimization strategies. Different colors correspond to different minimization intensities. So how many items do we actually leave in the user profile for an algorithm to observe? And on the y-axis, I have RMSE, which is one of the standard error metrics that quantifies the quality of the performance in recommendation setups. And so essentially, the observation we make here that, in general, the error distribution on a population level remains stable as we minimize across, and we've observed that across various minimization strategies. What I'm showing here is just a random minimization strategy. And second, we can actually minimize out large portions of data while keeping the quality. So for example, I can leave just 15 items in every user profile, and the quality is going to drop by a very small amount. We further observed that the robustness to minimization differs by the baseline algorithm. So when we change a recommender system from the KNN recommendation system that is based on the basis of predictions on the user neighborhood and how people rate products in the user's neighborhood to an SVD method that uses matrix factorization, we've observed that the situation when it comes to data minimization becomes even better. So we can throw away even more data and the quality of the predictions stays largely intact. And so it seems like the global data minimization is feasible. But we also are interested in what's actually happening for each of the users. And so what I'm plotting here on the right is exactly the same data as I'm plotting on the left. It's just that I'm sorting the error values differently. So now all the error values are just sorted by the performance of the algorithm, that is this black line, for the predictions made without any data minimization. And other error values correspond to the same user that is represented on the x-axis for the black line. So essentially what these two plots tell us together is that while minimization seems feasible globally, the error distribution stays the same, we can remove a lot of the data, this actually hides disparate impact to individual users. So the question becomes, can we somehow control who these users are, both individually and perhaps on the level of groups? What we did is we ran a regression analysis trying to understand the correlation between the error delta, that is how much error we are incurring by minimization, and different characteristics of the user that are sort of natural to model in the context of recommender systems. So these were things such as a number of ratings, average rating value, average popularity of items, number of genres in their profile, average similarity to other users. And we actually found no strong correlation between any of these characteristics and the error delta. Instead, what we found was that there are very complex interplays between individual user characteristics, the population data, the base recommendation algorithm that we use, so how a system is actually operating the service, and the minimization strategy that we use. So for instance, what we found in the context of SVD recommendations is that if we minimize the data by selecting items with the highest rating, the induced error will be higher for users who generally give lower ratings. While if we select the ratings with the lowest values to be observed by a recommendation algorithm from the user profiles, the error will be higher for users who generally give higher ratings. But this is a relationship that we only observed in this particular scenario, the algorithm and minimization strategy. In general, it's like very hard to control what is going to happen, both because of the complexity of the interplay between these different elements of the ecosystem. And there are other consequences that we've recently observed when it comes to impact on users when we minimize. So in another recent paper, we looked at active learning strategies for selecting features from user profiles when minimizing the data, so this is in an ongoing manner. And what we observed is that compared to the random minimization strategies, when we use active learning, the distribution of the amount of data that is collected from different users is very uneven. So there are lots of the users from whom we're collecting very little data, but there are a number of sort of high collection users from whom we're collecting as many as 500 or 600 ratings. So the question becomes, how do we balance this? Should our goal be to collect the same amount of data from each user? Should the user have the option to choose that they want to be a high collection user because for a promise that they're going to get a better quality service? So lots of interesting questions here as to how we should handle this situation. We also observed some other interesting effects that are consequential in terms of the actual implementation of this principle. So this is again in an active collection setting, and there is a lot on this plot, but what I essentially want you to focus on is that we compared different feature acquisition strategies, and random and different active feature acquisition strategies. And we compared what is going to be the effect on the minimization feasibility and accuracy, depending on how we initialize the data. Like what is this initial subset of data that the algorithm sees before it starts minimizing? And so we had a condition where we had a random selection across all of the data, all items and all users. And we also had conditions where we selected a full set of observations, but from a subset of users. And then another one where we selected a random set of observations, but by features. And so what we observed there is that active learning, the active feature acquisition strategies decrease their performance when we don't select features randomly. So essentially when we select only subsets of users or subsets of items to initialize. And the reason why I'm mentioning this is because there's a certain consequences in the way we're implementing these systems in the real world. The initializing with a subset of users scenario in this experiment corresponds to the situation where we have new users coming into the system as the system operates over a longer period of time. And initializing with a subset of items corresponds to the situation where, for example, the law forbids us to collect certain types of features, for example, gender or other types of features that might be unnecessary in a given context. So there are lots of considerations to make here when we decide whether and how we want to minimize. And this brings me almost to the last slide of this talk. And in this slide, what I want to do is more explicitly establish the connection between what I've talked about and the theme of this workshop. So what are some of the open questions in algorithmic fairness? Interestingly, the Article 5 of GDPR does not determine any hierarchy of different principles. So essentially, it says that data minimization is not superior to fairness or accuracy or vice versa. All of these principles have to be taken into account simultaneously. So I guess what that translates to for us is that we have to understand how to trade these different principles with each other in different systems. And in existing work, of course, there has been a lot of work that looks into the trade-off between fairness and accuracy. And in the data minimization work, both ours and other people's, we look at the trade-off between data minimization and accuracy as well. But because all of these principles have to be satisfied, or ideally should be satisfied at the same time, the question becomes, how do we trade off data minimization and fairness, and what would be formal approaches to this, and what are even some practical issues to focus on? And so far, what I've told you in this talk can be exactly mapped to this. Like, we have some empirical evidence as to what are some potential things to look at when we want to establish, like, what is the relationship between data minimization and fairness. So we have observed that there might be quality of service impact on individuals and groups. There might be data collection impact on individuals and groups. So we might have some high collection users and users from whom we don't collect as much data. And so lots of interesting questions there. And with this, I want to end the talk, and I'm happy to take your questions.
Thank you very much, Asha. So if there are questions, please raise your hand. I think I need to enable. Yeah, so we got a question.
Hello. Basically, the whole presentation makes very sense, and I'm against impossibilities as mentioned here. But the concern here probably will be the bootstrapping part. Basically, if you don't have the data to analyze and to estimate possibility for minimization, you are not able to estimate that. So what's your take on that part for introducing of new models and conflict on that respect?
Right. We actually have a working paper. Some of the results are presented here come from this paper, and we might be happy to share a preprint if you're interested. So they're essentially, in a lot of these empirical works that I mentioned at the beginning, what you observe is sort of like a power law relation between the error and the amount of data that you collect. So essentially, we leverage this insight to fit power law curves to the data that we observe, and that lets us sort of predict where in on this curve in terms of the error we are, and what can we hope for in terms of absolute error and absolute prediction, quality of predictions that we would be able to make. So that's one of the approaches we've taken so far, but you're absolutely right that this is one of the biggest challenges, like actually figuring out what is even possible in terms of the quality of service.
One of the thoughts that I had here during this presentation would be that we should have sort of smoothness of minimization, which basically means if you are bootstrapping a model, you have a small minimization effort. Basically, you are collecting an increasing data set. After reaching some outer bound of power law, you would increase the minimization to the maximum, something like that, probably.
It certainly corresponds to some of the empirical results we've observed. So essentially, the error differences are the biggest at the beginning. So I'm not sure if I understood your idea correctly, but what we essentially, or what our work essentially suggests, is that you might collect much more data at individual steps from each user initially. Because you know it's going to reduce error for sure, and then decrease the step. This is actually something we've observed in our work as well.
Thank you.
Yeah, thank you.
Masi?
Yes, hi. Thanks for the very interesting talk. I want to ask if there is, if you see any connections between what you're doing and meta-learning. I mean, with this I mean whether you can learn which data, what you need to measure, how many data points you need to measure, which features you need to measure for a new user, right? In order to minimize also this data collection, and maybe I don't know, you can take both accuracy and fairness into account into the process, and this would be one way to address the problem in your last slide, maybe.
Yeah, I think this is a great insight. And in fact, I think there is a connection between meta-learning and data minimization. We've actually stumbled upon a paper by MSR researchers from, I think, ICML 2017, if I remember correctly, that proposes meta-learning approaches that when you dig deeper into the actual details of what the method is doing are very similar to what we want to do here. So there is definitely a connection. And as I mentioned, what the approach we've taken so far for fitting these parallel curves to data that we observe is just one of the approaches. And it might be definitely possible to approach this in other ways. For example, just learning a model that would automatically comply with the data minimization. Yeah, I think it's a great idea.
Thanks.
Thank you.
So I think there's no more questions, but I have one, because you have been talking about data minimization, which, as far as I understand, is you first collect data and then you start removing. And I was wondering whether people have addressed the problem from actually the opposite way, where you don't have anything and you directly don't record data, but you only record strategically so that you can learn a model.
Yeah, so in our experiments, the SIG-IR paper presented earlier, we did assume we have an oracle that sees all of the data. In the second work, I talked about we make fewer assumptions about this. So we essentially say we don't have access to full user data to make any predictions, although there must be some mechanism that queries the data from the users. And this sort of is something that we said, okay, let's think how we implement this in practice in the future. So if I understand your question correctly, yes, I think it's one of the open questions for how to actually do this. Like how, when you don't even know what is there in the user data or what you can query for, which is very often the case, if the data resides on the user computer or has not been generated at all. So I have some latent learnings, latent ratings for different products that I might not have even recorded. I think it's a great point. How do we learn a model there when we don't even know what is possible to observe? I hope I understood your question correctly.
Yeah, you did. I mean, I guess also some of the works in the fairness literature, they also have talked about whether the company that develops the system actually have access to sensitive data, and how can you actually define a fair model without having access to such a sensitive data? So they enter this third role of a regulator or someone which have access to private data and basically can apply the existing model to see how things are going. So I'm not sure whether this is a framework that can somehow could be adapted to this setting too.
It's a great question. I don't think I have any thoughts about that, but I would definitely like to look into this. So if you could share some pointers, that would be great.
Sure.
I do want to mention, because I think there's maybe one more minute left. Data minimization should actually be applied in a number of different scenarios. So you should apply it as you collect data when you already know what your purpose is. But there is also a requirement to essentially delete the data as soon as the purpose has been satisfied. Now the question, what does that mean in different types of systems and different types of scenarios is of course it's an open question. But essentially what would happen there is exactly that you have access to all of the data that you have collected, and based on what is there in the system, you should decide what to get rid of because you don't need it anymore. So both of these scenarios actually have some corresponding reward scenarios as well.
I see. Okay, thank you very much. Asia, actually, thank you very much to Asia and all the speakers that participated in this first session. Right now, we are going to have 10 minutes break, and we will be coming back with the next speaker at 3:40. So see you in a bit.
Hello, everyone. This is Julian Ferres from Madrid, Spain, and it's my pleasure to help chairing this session. Next speaker is Mikhail Durochenkin. He's research staff member at IDM Research in Cambridge, Massachusetts, Boston. His research interests include Bayesian, modeling and inference, model fusion and federated learning, optimal transport, and algorithmic fairness. He's here with us in the audience, so you can share your screen and jump directly to your talk.
Hi, Julian. Thank you for the introduction. Hello, everyone. Thanks for this workshop and for opportunity to present. Let me share my screen. Okay. My name is Mikhail, and today's talk is about practical individual fairness algorithms. So I work at IBM Research and MIT IBM Watson AI Lab, and a lot of this work was done in collaboration with University of Michigan in Ann Arbor. So, I mean, we are here today and on Monday to talk about fairness, and we know that when we use algorithms to make decisions, that sometimes causes biases, and we try to come up with different ways to prevent those biases when we use algorithms. However, even like indeed, there is a history of regulations that try to enforce fairness in decision making. So especially in lending in the United States, there's Equal Credit Opportunity Act that's quite old by now. But despite that, in the recent years, if we look at the data from mortgages, we see that there is a significant bias between different racial groups. And well, despite the problems, we still think that we can fix those problems by approaching the problems mathematically, and we can maybe address the biases in algorithms using some techniques and the machine learning and statistics. So first, let's talk about what are the types of fairness that we have. So we already talked today about group fairness, and so the idea of group fairness is to make algorithms treat groups of individuals equally. And so mathematically, we can define it in terms of different types of conditional dependencies. So for instance, equalized odds says that our prediction conditioned on the true class should be independent of the protected attribute. And while the group fairness is, there is still a lot more work to do, it's also something that has been fairly well studied in the literature. The other type of fairness that I'd like to talk about today is individual fairness. So the basic premise is that we want algorithms to treat similar individuals similarly. So for instance, let's say we have two loan applicants. So Ryan that earns 50,000 and lives in a predominantly white zip code area, and Tari who earns the same amount of money but lives in a different zip code area. So these two individuals are similar from the perspective of deciding whether to give them a loan or not. But if the algorithm decides to give a loan to Ryan but not to Tari, that is a violation of individual fairness because the individuals are similar, but the outcomes are different. So we want to make sure that the outcomes for both are similar, whether it's an acceptance or rejection of a loan application, but they should be the same. So to be more formal, the individual fairness says that given a machine learning model H, we want to enforce this kind of a Lipschitz condition where the outputs of the model, so dy is a metric on the outputs, so it's, let's say for regression could be simple like square distance, or it could be tail divergence for classification. So we want to make sure that it is bounded by the distance between the inputs. However, the distance between the inputs here is not as simple, so it is something called a fair metric. So, and it depends on the application we are considering. And while this is a very interesting topic on its own, I will not be talking a lot about fair metric today, but there is a growing amount of literature on that as well. So first, let's look at an example. So what is the possible difference between individual and group fairness? Why should we treat them separately? And in this example, we'll see how individual fairness could be a more relevant notion of fairness for the problem. So let's look at a sentiment analysis. So we want to classify words as positive or negative. It's a very simple NLP task by nowadays. So positive words are admire, adorable, joy, and so on. Negative, aggressive, distrust. And so, as I said, it's an easy problem. We can use deep learning, word embeddings. It's very easy to get 95% test accuracy. The question is, well, did we succeed? And remember, there were no protected attributes involved, or similarly, the problem is not even so much related to fairness. But we can start deploying this problem in practice where the text could easily contain the names of people. And let's say we look at the groups of names which are more typical among the European American population and among the African American population. So, for example, Adam versus Tari, and so on. And so when we deploy the system, it will also try to assign sentiment to the names of people if text has a name in it. And so what we can observe is that, well, the average sentiment of the European American names is much higher than the average sentiment of the African American names. So that is a violation of group fairness, and we can fix it. So for instance, hypothetically, we can align the averages. So the second pair of bar charts satisfies group fairness because on average, the sentiment for both groups is the same. However, this didn't quite fix the problem for Ryan and Tyree. So especially in particular for Tyree, because his name is still assigned a very low sentiment score, unlike Ryan's, which assigned a very high sentiment score. And in this case, we consider all names to be similar. So we want them to have a similar sentiment scores. So if we use individual fairness, so we can achieve actually the equality. So you can see that we not only need to align the means, but also we need to align the variances. So we need to reduce the variances. This way, the sentiment scores for all of the names that we are considering is the same. So that is the way to satisfy individual fairness. And we can maintain the accuracy at the same time. So from the original 95%, it goes down to 94%, which perhaps is acceptable trade-off to achieve fairness in this application. So this example shows how sometimes individual fairness or like group fairness could be not enough, and we want to consider individual fairness in certain applications. Okay, so how did we get there? So in order to formulate a practical notions of individual fairness, we first appealed to the distribution and robust optimization. And we defined this objective function, which basically says we want to minimize the loss. So we're going to minimize whatever is on the slide. So we want to minimize the loss not only on the empirical data distribution Pn, but also on all data distributions which are similar to Pn. And similar in the sense of a Wasserstein distance, but Wasserstein distance with the ground cost being not the Euclidean or something, but the fair metric here. So essentially, we consider all the data sets which are similar in fair metric to the data set we have, and then we want to make sure that the loss is small on all of them. This was our first approach. This is the one that this one called sensor that I've showed on the previous slide, and as we saw, it could be effective, but it is somewhat different from the original definition of individual fairness. And the other problem is that it combines sort of accuracy and fairness into one quantity, which is not always desirable. So our second pass at the problem, we define this new notion, which we call distributional individual fairness, DIF. And so in this case, we separate the loss function. So there is no loss function involved here. And the definition is kind of more in line with the original definition of individual fairness. So it also is based on optimal transport. So basically, we define this quantity DIF of a machine learning model H, which is equal to, so we want to find the map, the optimal transport map between our inputs such that they're still similar. So that's the constraint in the second line, but at the same time, the difference between the outputs is big. So essentially, we try to look again at all the data that's similar to the data we have, and then find the ones where the machine learning performs differently in comparison to the original data. So essentially, what we want to enforce is that on average, for inputs that are on distance epsilon in fair metric to our data, so if you minimize this quantity, that the outputs are also similar. So some comment on sort of relation to the original individual fairness definition. So if you remember, the original individual fairness definition is per point versus we define it for the distributions. And I mean, there are many differences. So in a sense, this is an expectation and that one is not. But one, I wanted to highlight that the original individual fairness does not necessarily include the DIF. And this can be seen from defining this transportation map T, individual fairness, such that it basically finds the transportation per point. So for each input point, we find a point within distance epsilon that maximizes the distance in the outputs. And we can see that this is a feasible map, but it's not necessarily optimal because the DIF definition allows transporting some points by more than epsilon, because we only want the distance epsilon on average, so some points could be transported by distance more than epsilon. So in this sense, DIF is more stringent than original individual fairness definition. But of course, it is not stringent in all the ways. So they're just, I mean, they're comparable, but one not include the other. Okay, so how do we train the models that satisfy DIF? So the idea is pretty simple. We just will use it as a regularizer. So we have a loss function and we add DIF regularizer with some coefficient rho, which will define the strengths of the regularization. And the coefficient rho, as we shall see later in the experiments, is essentially defines the fairness accuracy trade-off that we can achieve. So here again, we have a model class H, some, for example, neural networks with certain architecture. We'll have a loss function and the strengths of regularization for the fairness. So this problem, I mean, if you remember the definition of DIFs, then that kind of was pretty complicated, involves some transportation maps and so on. So indeed, it is not that hard. So if you look at the dual of this problem, it is a univariate problem. So where the term, so it's basically the infimum over dual variable lambda of this quantity, and the key there is that this and x. So this is a supremum. So essentially what it does is that it says, well, let's take the original point x, and then let's find the point x prime such that the output of the model is very different. But at the same time, we want it to be close to the original point x. So this comes from the fact that we have we want to maximize the distance between the outputs minus the distance between the inputs. So this, I mean, this is an inner optimization problem to solve, but it's not very hard to solve. It can be solved using basically this adversarial attack. So we just, you know, maximize the difference in outputs of the model with respect to the inputs. So that's something people have been already doing for several years. So as long as we can write our objective function as an expectation, we know it is amendable to stochastic optimization, which is the case here. So we can say, okay, we have parameter theta, which is the weights of a neural network, and we have a dual variable lambda. And so we want to minimize the expectation of this function f, which is basically the loss plus the dual objective function. So this way we can train it on a large scale data sets and you know, kind of applies its technique in practice. So to see how this works in a toy data, let's imagine this hypothetical situation. We just have a two-dimensional data set, so the x and y axis, and we decide that the points on horizontal lines, so which have the same y-axis values, are similar. So this is our fair metric, but the training data is biased. So basically, the probability of y given x is not constant on horizontal lines. And so we will use our regularizer to correct bias in the data. So here is a very small value of the regularizer. So here's the colors, the circles, triangles, and red, blue colors are different classes. So we fit like a simple neural network to this two-dimensional data, and we see this is pretty accurate. but it's the decision function is not constant along the horizontal lines. And this means that it does not satisfy the individual fairness here. I mean, of course, this is just a hypothetical situation for demonstration. So we can increase the regularizer value, so the strength of the DIF regularizer, and we see that the decision boundary becomes flatter. So essentially it becomes more fair with respect to this fair metric. And we can continue increasing it, and eventually, like, I mean, of course, we lose some accuracy because the original classifier was the most accurate, but at the end of the day, our decision function is constant on the horizontal lines, so which means that we can satisfy the individual fairness in this case. So let's also go over some examples on real data. So first one is a toxic comment classification challenge. So this is a relatively large data set. It's I think after pre-processing, so we were left with about 165,000 text comments. And the task is to predict if a comment is toxic or not. So this is basically needed for hate speech detection in the online discussions to make them more inclusive. So how do we measure individual fairness here? So we don't now have a fair metric as in the simulation example. So the way we do it is by basically counting how often a prediction changes when we change the certain identity tokens in the text. And the identity tokens are different words, such as like a Christian, gay, lesbian, and so on. So for example, is the prediction for the comment some people are gay is the same for the comment some people are straight? And there are 50 identity tokens, so we only consider the individual fairness satisfied if the prediction is the same across all 50 variations of a given sentence. So basically we say some people are gay, and then we change it to some people are Christian, some people are white, some people are black, and so on. And there are many of those tokens. And if the prediction is the same on all of them, then it means the individual fairness is satisfied. And then you basically just count the proportion of test comments on which the prediction is the same for all 50 variations. And so we also test here how does the increase in the regularization strengths affects the performance. So as I mentioned before, this formulation achieves us a clear decoupling of accuracy and fairness. And we see as we increase the regularization strengths, the balanced accuracy decreases versus prediction consistency, which is basically the percentage of comments where the prediction didn't change on all the 50 variations, increases. So in practice, the user can consider different regulation strengths depending on what they try to achieve. And so also to sort of mention what happened behind the scenes is that we use BERT. So we use like a big machine learning model. So it is kind of pretty scalable and applicable to pretty large problems. So another data set that we looked at is the bias in bias data set. So it's even a bigger one. So it's 400,000 textual biodescriptions, and we have 28 classes here. And again, we measure individual fairness in a similar way. So we change the names and gender pronouns in a bio and see if the prediction has changed, and again, measure this prediction consistency, as we call it. So in this case, again, we see as we increase regularization strengths, the prediction consistency increases. So it means that the fairness improves. In this case, the balanced accuracy doesn't really suffer so much. So I mean, the y-axis range is pretty small, but basically it even increases at the beginning and then starts to decrease. So that somewhat suggests that maybe sometimes it is possible that trying to enforce fairness could also help with the performance. For instance, in this data set, like there is a very little amount of male nurses. So it meaning that like we do not predict male nurses very well, but then once we enforce fairness, we start the algorithm performs better on male nurses. So this is so I presented basically mostly the supervised learning context problem, but this idea can be also extended to ranking, and we can also perform hypothesis testing using these techniques. So this is all based on either the distribution robust formulation that I presented first or the DIF formulation that I presented second. So this allows us to sort of solve the whole suite of problems related to individual fairness. And if you want to learn more, let's say you want to learn about ranking, also feel free to join our presentation at iClear this year in May. So we will be talking about ranking and some of the hypothesis testing problems. And so I still have a couple more minutes, right?
Yes, we have some time for questions. So if there is some question.
I can also talk, or yeah, I can talk a little bit about the FAIR metric, I think, quickly. So I didn't really talk where do we get the FAIR metric, but just to give an idea. So we had this example of Ryan and Therese that we define as similar, but that's like kind of, we just looked at them and like it was an example, of course. So in practice, it could be quite challenging. So we need a lot of subject expertise, we need a lot of time, and on some data types, it could be pretty hard. Like we're not gonna, be creating new images and stuff like that. So one idea that we used in actually throughout these examples is a pretty simple one. So perhaps in a future work, something better can be, something more sophisticated can be done, but we use the Mahalanobis type metric. And the idea is to basically fit a logistic regression type of model to the pairs of samples. So we expect that the input data could be like a comparable or incomparable samples, and then we fit a logistic regression to find the sigma in the Mahalanobis distance that can predict the similarity of the input samples. So the example here is the lone applicants with similar income, such as Ryan and Terry, that you had throughout the talk. And then the other approach that we used, for instance, in this bias and toxicity examples and in the names examples as well. So it's pretty useful for the text data with word embeddings or some other embeddings, is again to fit a Mahalanobis type metric. But in this case, suppose we have a groups of comparable samples, or let's say we just have one group. So let's say we have the names that you were considering, or we have like just a separate data set of names. And so because we know that all of them are comparable, we know that any variation in that data is something that we would like to ignore. So we can simply fit a PCA model to it and then basically define a metric that ignores the subspace spanned by the principal components. Okay, so this is a brief tour of the FAIR metric, and I'm happy to take any questions. Thank you for the attention.
Yes, please raise your hands if you want to just jump or type the question in the chat. We have like 5-10 minutes for questions, so we are ahead of time.
I believe Samira has a question. Samira, do you want to mute yourself and speak up? Let me find you.
Okay, now I'm allowed. Like it told me that the host didn't allow me. Yeah, this was very interesting. I had a quick question out of curiosity because you worked with this data a lot. Did it happen to you that for some demographic groups, you saw that the dialect in that demographic group affected like their score or like their sentiment score in general? So did it happen that, for example, for example, for African Americans, it could be that their dialect seems like aggressive, although it's not. It's just the way the kind of words that they could use. And then I can imagine that like no matter how you switch this sensitive feature that you had, for example, you talked about gay, lesbian, Christian, that the score would remain low compared to like similar sentences in other demographic groups.
I see. Yeah, thank you for the question. We haven't, to be honest, we haven't looked at that, so it would be an interesting problem. So right now, the problem, is even more basic, I would say. So I think what you're talking about is a more sophisticated issue. So right now, the problem is just simply that a lot of comments that have the word like gay in it or some of the other identity tokens, they're toxic. They're labeled as toxic in the training data. So the model just learns that the word gay implies toxicity. So,
right.
But what you mentioned about the style of the writing and the whole sentence also possibly causing some biases, it's even more nuanced. So yes, we haven't got there yet.
Yeah. No, I was just
curious,
maybe you just saw it when you were looking at the data. Thanks.
More questions? I also have one question. Misha, this is more philosophical. When comparing group fairness to individual fairness, it's obvious that individual fairness, if properly targeted, it's much better to really approach the problem at individual terms. So is individual fairness the only way ahead? Is the only thing we should pursue in the future, individual fairness? Or is there some place or some application where group fairness still is the best approach to seek? So what is your kind of, what is the applicability of group fairness and individual fairness? Can we go into our research in both directions and make both directions applicable and productive?
Mm-hmm. Thank you. Yes, I think, I mean, I also work on some group fairness projects, so I totally think that both are important, but I think it's worth mentioning in this context sort of subgroup fairness, because so subgroup fairness is something that basically interpolates between group and individual fairness and makes them connected rather than just like two very different definitions of fairness. And I think some of the problems with the group fairness, that if you just simply look at a one protected attribute, is that we could miss a lot of other groups in the data, and we can end up sort of satisfying group fairness, but at the same time we cause even worse problems. So I think being careful about the subgroups and like using more protected attributes than just one, and like, you know, thinking more carefully about it is maybe a way to kind of merge group fairness and individual fairness into something that will be the most applicable.
Okay.
And I think, because I think that the most basic sort of form of group fairness is good. I mean, that's something we want to have, but the problem is that among the models that satisfy the group fairness, there are good ones, the ones we want, but there are also bad ones. So we just want to make sure that, you know, the ones we get in the end is not the bad one.
Okay. More questions from the audience? If not, thank you very much for your talk. And then I think we can go on with the next speaker, Aaron Roth. Aaron, are you here?
I'm here, yeah. You want me to start
Hello,
sharing
Aaron.
my screen?
So Aaron is professor of computer and information science at the University of Pennsylvania in Philadelphia. He studies algorithms and machine learning, especially in the areas of private data analysis, fairness in machine learning, and game theory. So thank you for accepting this, being a speaker here, and please go.
All right, yeah, thanks for having me. And I'm going to talk about some joint work with a bunch of my excellent colleagues pictured here. And this will maybe tie into the discussion we were just having in the Q&A about sort of the relationship between promises that really bind for individuals and promises that bind only for large course groups, and maybe sort of the statistically feasible region in between. So our goal in this project is sort of a basic and fundamental one that doesn't necessarily have fairness in its description, although you'll see in a moment it's quite closely related to issues of fairness and equity. But our goal is to, at a basic level, endow sequential predictions with estimates of uncertainty, like prediction intervals or variance estimates, without having to make any assumptions about the data. And, you know, okay, like on the one hand, we know some techniques for how to do this, you know, like this is what conformal prediction does, for example, you know, except that it makes assumptions about the data. But as I'll talk about in a moment, the kinds of uncertainty estimates that tools like conformal predictions make have little promise to individuals or even large structured subgroups, and that's also something we're going to want to fix. Okay, so just to sort of get everyone on the same page, let's sort of imagine the following toy scenario. Suppose that there's, I don't know, a global pandemic, and hospitals are strained for resources, and so they need to figure out a way of triaging resources, and maybe they've got a statistical model that will predict, say, a patient's predicted prognosis in 2 days' time, so they can use that information to triage like ICU resources, for example. And because these are important decisions, they want to not just make point predictions, but they want to have uncertainty estimates associated with their predictions. So, for example, you might go into the doctor's office and she might tell you, well, you know, given your features X, the sort of medical history we have about you, our model predicts that your expected disease severity in 2 days' time is something, f of x. Okay, and this is important. It's going to inform what kinds of resources you're given. And so you might ask your doctor, well, how sure are you about that? And there's various things she might tell you, but for example, she could say, well, our model gives a 95% prediction interval that your disease severity will be between some lower bound and some upper bound, prediction interval. And then you think to yourself, okay, like what does that prediction interval mean? Okay, and so let's talk about what you might hope it means and then probably what it really means. So in an idealized world, you would hope that all of the predictions that are made about you, okay, so f of x, the prediction of your mean disease severity, and this prediction interval, which is an uncertainty estimate for your disease severity, you would hope that these are sort of individualized or conditional estimates, meaning you sort of hope that f of x is the true conditional distribution on your label, conditional on all observable information about you, and that this prediction interval sort of says, okay, well, conditioning on everything we know about you with probability 95% somehow over the unrealized or unmeasured randomness of the world, your label will fall within this interval. That's sort of like what you really want these probabilities to mean, because then you can really think of them as probabilities specific to you, and you can, make decisions, perform various, like utility maximization calculations, so on and so forth. But if you think about it, strictly speaking, like in a large feature space, that's never what these estimates mean, because it's impossible to come up with estimates for conditional probabilities. In a large feature space, you are likely the only person we've ever seen who has exactly your medical history, who has exactly your features X. And so again, like strictly speaking, without making heroic assumptions about how the world works, we have seen somewhere between like 0 and 1 sample of the distribution on labels conditional on all of your features. And so strictly speaking, we cannot promise anything about the mean of this distribution or about its tails. And so what these estimates generally mean in practice are they're not conditional estimates, they're what are called marginal estimates. So at best, an estimate of an expectation is typically calibrated. We'll talk about in detail what that means in a few slides, but think of it as a guarantee that the estimate is correct on average, as averaged over all of the people who got the same prediction as you. Similarly, a prediction interval, if we came up with it using a conformal prediction method, for example, will be a marginal prediction interval. And what that means is, rather than averaging over the unrealized or unmeasured randomness of the world, conditional on your features, what we are doing is averaging over people, right? Even though it sort of looks syntactically the same, a marginal prediction interval is a very different promise. It says for 95% of people, their label is contained within the interval. Okay, so if you just sort of take standard machine learning techniques, like at best F is going to be calibrated, at best your prediction intervals are going to be marginal prediction intervals. And so the question is, should you be happy with that? So let's go back to our doctor-patient scenario. So, the doctor tells you, okay, I've got this 95% prediction interval, it's got bounds between L and U. And you might think to yourself, well, I'm part of a demographic group representing less than 5% of the population. And that's sort of a problem for interpreting a marginal prediction interval like this, because again, strictly speaking, it is entirely consistent that the prediction interval that the doctor gave you really is a valid 95% marginal prediction interval, but that it is always wrong for not just you, but for people like you, for people in your demographic group. Because the promise of a marginal prediction interval is just that it, fails to cover each person's label 5% of the time, but it says nothing about which people it fails for. So it might fail 100% of the time, for example, on a structured subgroup representing 5% of the population. Okay, Now, we don't, run just one medical study. We could, run clinical trials on different demographic groups. And so you could imagine asking the doctor, okay, well, what about for people like me? And she might even have an answer for you, right? Or several answers. She could flip through her medical journal and she could say, well, for African Americans under the age of 50, the 95% prediction interval is from A to B. And for women with a family history of diabetes, the 95% prediction interval is between C and D. And for people with egg allergies and no history of smoking, the 95% prediction interval is between E and F. And again, the problem is you might be a member simultaneously of all of these groups of people, right? These are not disjoint groups of people. You might be a member of all of these groups of people, but again, the guarantees of a marginal prediction interval are consistent with, for example, A to B being entirely disjoint from E to F. And so how do you, if you're a member of all of these demographic groups, even if a study has been conducted separately for each of them, how should you as an individual interpret guarantees of this sort? Okay. So that's sort of one problem that we want to fix. Let me point to sort of another problem we want to fix, which is that if you sort of take standard techniques from the literature, like conformal prediction, these are techniques for sort of sequential decision making. They tend to make very strong assumptions. In particular, they assume that, as much of machine learning does, the future should look like the past. So the data should be IID or at least exchangeable. But it's often not. So just to list some reasons, there might be covariate shift. So as a pandemic moves through different parts of the population, the demographics of patients arriving at the hospital can suddenly change in unanticipated ways. There can be label shift as treatments improve. The distribution on labels, conditional on features, can change. There could be strategic effects. If we're making decisions that have impact on people's lives, like lending or hiring or college admissions, people might manipulate their features to optimize for the deployed classifier. And so as you change your classifier, the features change. And of course, if the thing that you're trying to predict is time series data, like what is your condition as a function of the progression of your disease, well, then sort of right away, the data is not IID or exchangeable. And so we'd also like to fix this problem. Okay, so what we do here is we sort of mitigate both of these problems for sequential prediction. So we're going to do two things. We're going to, in an online sequential setting, we're going to predict things like means and variances and coverage intervals, prediction intervals that are going to give stronger than marginal guarantees in a sense that I'll make precise. And we'll do so in an adversarial set. We're going to assume nothing about the data. And so in particular, we can handle all of these ways in which the data might change over time in unexpected ways. So I think that maybe the headline result is for prediction intervals. This is sort of attacking the same problem that the conformal prediction literature sets out to solve. But we give a very general technique for doing this. And along the way, we give similar results for predicting means and variances and other higher moments of the label distribution. And those are the distributional properties that we sort of thought of as interesting. But you'll see, I'll only have time to briefly mention the techniques, but they're sort of quite general. So it's likely that if you have some distributional quantity, the same set of tools can be used to predict it in a multi-valid way. Okay, so before I tell you about what multi-valid prediction intervals are, let me tell you what mean multi-calibration is, sort of the equivalent notion for predicting means that you might have heard about. It's from a very nice paper from a few years ago. And this is sort of like the simplest setting. And in fact, we'll mostly derive in this talk an algorithm for obtaining mean multi-calibration in an online adversarial setting. And then we'll sort of see that the same results extend to other kinds of predictions. Okay, so let's give some notation. So we're operating in a sequential setting. So what we're going to see are sequences of feature label pairs. So every day we're going to see some feature vector X from some, abstract data domain. And it will be paired with a real valued label that I'm just going to imagine is scaled to lie between 0 and 1 for this talk. Okay, and we see over a sequence of t days examples like this. So we'll eventually see a sequence of t such examples. Now, every day we want to make some prediction. So after seeing the features, we're going to predict the label without knowing it yet. And so every day we will make a prediction, which I'll call y bar, which is also going to be a number between 0 and 1. And we're going to want these predictions to be somehow accurate. So let's build up some vocabulary if you're talking about how they might be accurate. And the first thing I want to talk about is mean consistency. They should be sort of right on average. So suppose I'm given some subset of people, some subset of the feature space. So maybe think about S as a demographic group that you care about. Okay. So mu of S is going to be the average, or in this case, the sum of the true labels for the people in demographic group S. Okay, so mu of S is just the actual, the sum of the actual labels for the people in S. In contrast, mu bar of S is the sum of the predictions for the people in S. Okay, and if we were making perfect predictions, then these would be the same thing, right? Because the sort of labels would, our predicted labels would equal the real labels. And so our first notion of mean consistency is just that our predictions should be right on average on a particular set. Okay, so we'll say that a predictor, mu, is mean consistent on a set, a predictor of mu, so this should be mu bar here, is mean consistent on a set if mu of S, the sum of the true labels, is equal to mu bar of S, the sum of the predicted labels. Okay, so if we were perfectly predicting things at an individual level, maybe if y bar equaled y, then in particular, our average predictions would be identical over any set. And here we're asking for something necessarily weaker than this sort of individual level correctness, which is of course impossible. And we're asking for sort of correctness on average over a set. Okay, so on average, our predictions on this set S should equal the true labels on this set S. And we can also define an approximate notion of this, right? Alpha mean consistency will allow some slack depending on alpha. Okay, so what's calibration? So to define calibration, we have to talk about a discretization of the real interval, right? So the labels are real numbers. They can lie between 0 and 1, and our predictions are also going to be real numbers. They can lie between 0 and 1. But calibration will be defined at some granularity, defined by like a discretization parameter m, which defines the sort of uniform grid of the unit interval corresponding to points 0, 1 over m, 2 over m, so on and so forth. So the bigger m is, the finer the granularity we're considering. And we will write b of I for the ith bucket, which sort of corresponds to the set of predicted labels that are closest to the grid point I over m than to any other grid point. So we will say that a prediction, y bar, is in the ith bucket if it's closer to I over m than to any other grid point. And finally, given a group of people S, think about this again as a demographic group, say, S of I, define S of I to be just the set of people in demographic group S whose predictions fell into the ith bucket. Okay, so it's a subset of a demographic group sliced along how we made predictions. Okay. So finally, a sequence of predictions that we've made is calibrated in sort of the standard usual sense if it satisfies mean consistency on all of the groups Xi, meaning just on the set of all possible people for whom we made a prediction in bucket I simultaneously for all I. Yeah, okay, so like in the sort of standard like weather prediction example, calibration means that on all days on which I predicted a 10% chance of rain, it should have rained 10% of the time. On all days in which I predicted a 20% chance of rain, it should have rained 20% of the time, right? And in this case, I'm like averaging over all people, okay? And then multi-calibration is sort of the natural extension. And it says, okay, well, give me some arbitrary, possibly very large collection of overlapping demographic groups. We'll call these G. What it means that a set of predictions is multi-calibrated is that it should be calibrated not just overall, but it should also be calibrated when I sort of zoom in on each of these demographic groups simultaneously for all of the demographic groups in my set. So it should also be calibrated on each group, which means that I want mean consistency on the set SI for every bucket my prediction might fall into, I, and for every demographic group. Okay, so that's multi-calibration. It's asking for these sort of distributional consistency constraints, sort of correctness on average, but like simultaneously over like a huge number of groups that are defined both by our prediction and on the demographics that a person might be a member of. And so with this idea in mind, we can see that we can generalize it. That was sort of the idea for means, but we can define the same thing for variances or other moments. We can define the same thing for prediction intervals. Let me just give you an example and go through this exercise of defining what we might want for prediction intervals. Okay. So again, we're given a sequence of examples. Okay. And now every day, the thing that we are predicting is an interval. Okay, we're saying, okay, today I think there's a 95% probability that the label will fall between some lower bound and some upper bound. And again, we'll talk about some discretization. These lower bounds and upper bounds are like real numbers, but we'll say that a particular prediction interval is in bucket ij if its lower end falls in bucket I and its upper end falls in bucket j. And now, sort of generalizing the same kind of idea that we saw with multi-calibration, we can say that a sequence of prediction intervals are multi-valid if, for our favorite coverage target, like 95%, say we want to cover the labels 95% of the time, and for a particular collection of demographic groups, okay, again, this can be very large, it can be a set of overlapping demographic groups. And for every bucket in which our prediction intervals might fall, right, it should hold that for every single demographic group, when I look at the fraction of the time I actually covered the label, the realized label, amongst the set of people who fell into demographic group S and for whom I made a prediction, of a prediction interval falling into a particular bucket, well, I asserted it was supposed to be a 95% prediction interval. It really should be, meaning the empirical fraction of the time I cover their label should be 95%, or more generally 1 minus delta. And in general, you can define some approximate notion of this that allows the deviation from exact coverage to differ by something that depends on alpha. Okay. And finally, what's the problem that we want to solve? It's an online problem. Every day, an adversary shows us a new person represented by some feature vector. And the adversary chooses a label for that person, but doesn't show it to the learner. Now, the learner has to make some prediction. In general, the prediction could be a mean or a variance or a prediction interval, and the learner is allowed to use randomness. And the learner is then going to observe the label only after they make their prediction. So our goal is to show how to make predictions so that in the worst case over adversaries, our empirical sequence of predictions are multi-valid in whichever way we want to talk about. So if we're predicting means, we want multi-calibration. If we're predicting prediction intervals, we want multi-validity, and we can talk about other distributional quantities as well. Okay, so how do you do it? I've only got 10 minutes, so let me, in fact, I think how you do it is the most interesting part, but let me give you sort of a teaser for it, and I'll point you to the paper if you're interested. So you can think of, and let's talk about mean multi-calibration. We can do this for sort of all of these notions, but mean multi-calibration is the simplest and I think gets the basic ideas across. So you can think about mean multi-calibration as defined by a whole bunch of constraints on the sequence of predictions that you make. Defined, one constraint for each demographic group S that you care about and for each bucket on which we're defining calibration. Okay, and so we can enunciate these constraints in terms of these quantities V, again, defined one for each demographic group and for each bucket in which our prediction might fall. And V just sort of accumulates, it counts across all of the days in which the person who showed up was in that day was in demographic group S, and in which the label we predicted was in bucket I, of the sort of error of our prediction, the difference between our predicted label and the true label. And these quantities are defined such that if at the end of time, after our full sequence of interactions, the absolute value of these quantities is all small, one for each demographic group and for each prediction, then our sequence of predictions will have been multi-calibrated. That's sort of how we defined things. Okay, so what are we going to do? We want to design an algorithm that is able to guarantee that sort of against any adversary at the end of time, the maximum absolute value of these V quantities maximized over all demographic groups and over all buckets I is small. But this is sort of a fiddly quantity to think about because it depends on the whole history. Like things that the algorithm does today might affect what happens to this quantity, 10 days from now. And so it's like hard to think about that. And so instead we can try to think about sort of a greedy strategy. Suppose we could come up with an algorithm that guaranteed that for any X, for any feature vector we might see, if we get to make our decisions after seeing the feature vector, that the expected increase in this loss function would be small. Okay, if we could come up with an algorithm that sort of could greedily promise for any history, for any new person who shows up, we can make a prediction so that the expected increase in this loss is small, then we're good to go because we can just telescope, these terms, and we'll end up with a bound on the final loss, the quantity that we wanted. And let me now briefly remind you what a zero-sum game is, because this is going to be very important. So a zero-sum game is defined by three things. There's a minimization player who's got some strategy space, A1. There's a maximization player who's got some strategy space, A2, and there's a utility function, okay? And the players are allowed to randomize, so we can talk about distributions over the action space of the minimization player and the maximization player. And the minimization player wants to minimize this utility function, and the maximization player wants to maximize it. And we're going to identify the minimization player with the learner here, and the maximization player with the adversary. And the one thing you need to know about zero-sum games, like the sort of crucial defining thing about zero-sum games, is that the order of play doesn't matter. This is von Neumann's minimax theorem. And it says that if we're playing a zero-sum game, rock, paper, scissors, you can force me to announce my strategy to you ahead of time, or I can force you to announce your strategy to me ahead of time, allowing the other player the advantage of best responding. And if it's a zero-sum game, it doesn't matter. How well I can do is independent of whether I'm forced to go first or whether I'm allowed to go second. Okay, I have to announce a randomized strategy, of course, but this is sort of the special thing about zero-sum games. Okay, and so here's at a 10,000-foot view the idea. At every round, we're going to define a game between the learner and the adversary. The learner's strategy space is their predictions. The adversary's strategy space are the labels they can come up with. And the utility function is going to be this quantity, which is the increase in loss, the one-round increase in loss. This is the thing that we are trying to keep small as the algorithm designer. And so the algorithm would like to minimize this quantity and the adversary would like to maximize it. And now we imagine that the adversary goes first, right? In what's actually happening, the learner goes first because we have to commit to an algorithm first, then the adversary can choose a worst case sequence. But imagine that the adversary goes first. And the thing about zero-sum games is we're allowed to analyze the game imagining the adversary goes first. And what that means is that the adversary first tells us a distribution over labels, right? It tells us the true distribution over labels. And if you sort of think about it, this makes the problem of calibration, even individual level calibration, extremely easy. Because if I know the true distribution on labels for the person who showed up today, then I can just predict the mean of this distribution. And thinking forward a bit, I could predict a 95%, conditional prediction interval, or I could predict the variance or anything else I like. And so when you think about the adversary as first having to announce to you the true label distribution, it becomes sort of clear that it's easy to give an algorithm that satisfies multi-calibration or multi-validity or what have you. Now, of course, that's not how the world actually works. We have to commit to the algorithm first. But the minimax theorem, in a non-constructive way, allows us to conclude that the learner can do just as well, even if they're forced to commit to their strategy first. Which means there's an actual algorithm you can come up with, although this argument doesn't give it to you, that promises that it does well against a worst case adversary. Okay, so we get a theorem. You can get multi-calibration with actually very good constants. There's no hidden constants here. And when it comes time to come up with a concrete algorithm, okay, it takes some doing, but in some sense, what you have to do is set out before you already. Like you just have to compute the equilibrium strategy of this game that we defined. And the only thing I want to highlight here is that the algorithm is extremely simple. It's sort of an elementary algorithm, and this is what comes out of just put your head down and compute the equilibrium strategy. And in fact, it's almost deterministic. It randomizes just a little bit between adjacent predictions at the margin. Okay. Almost out of time, so let me just tell you that you can perform the same exercise for statistics that aren't just means. Or in sort of, at the 10,000 foot view, at least, of how I've told you how we do it, it's sort of clear why that is. Once the adversary commits to their distribution, I can predict all sorts of things. And so you can do exactly the same thing, for example, for prediction intervals. Again, once you do that, you can sort of churn through the equilibrium computation and you can get an efficient algorithm for solving the problem for prediction intervals. All right. I've got 5 minutes till the end, and so let me leave a couple of times for questions. Thanks.
Thank you, Aaron. Yeah, we have 5 minutes for questions, so you can raise your hands or write your questions in the chat for Aaron. Yeah, we have Pretty, so you can
hi.
Jump.
Yeah, thanks for a nice talk. I had a question relating to this first example that you gave about this 95% interval and somebody belonging to this 5% demographic group, right? So I was wondering to what extent would quantifying the source of uncertainty help, as in the uncertainty could be epistemic in the form of lack of knowledge, as in there are not enough samples related to the person here, as in not enough samples of people who are similar to you, versus this uncertainty could just be alietic due to inherent stochasticity. So whether it would help to identify what form of uncertainty we have.
Yes, so the nice thing, I guess, about prediction intervals and quantifications of uncertainty is that, of course, it's nice to be able to figure out these different kinds of uncertainty, but you don't need to in order to sort of win at the game as defined, in that, whatever the source of uncertainty is, if I can make predictions that cover the labels, say 95% of the time, then I've sort of succeeded at the goal. When you move to this sort of multi-validity setting, maybe it's sort of getting a little bit more towards the question you're asking, in that, although I didn't have time to talk about it, the guarantees you get do degrade with the size of the subgroup. And so, you get predictions, like you individually would get a prediction that you could interpret at your option as an average over any of the demographic groups for which you are a member. But you would sort of need to understand that if you wanted to interpret it as an average over a smaller demographic group, it would have higher error. And so that sort of at least isolates one sort of source of uncertainty, which is sort of the number of people we've seen who look like you like you, meaning part of some well-defined demographic group.
So we have also a question from Krishna. So we have just 2 minutes before the break. So please go, Krishna. If more questions, then the other questions can then wait after the break for the discussion table that we are going to open. But for now, Krishna, last question.
Okay, I'll keep it brief. Thanks, Aaron, for a great talk. Really enjoyed it. I had somewhat of a maybe small clarification question and then another related one. So the assumption here is that the knowledge of the groups and all the features of the users are known ahead of time, right? And there is no playing of games in terms of revealing the group membership or other things at different points of time. Correct.
Sort of as stated, that's right. So, although actually the way the algorithm works, if you decide, halfway through that you care about some other group, it's sort of actually no problem to just, hot patch it in, basically.
I see. And slightly related to this is, does this sort of, in these sequential decision-making situations, is there a concern about some sort of individual fairness related to the timing when somebody is getting a prediction? That means, it seems like it is possible that the same person, if they were positioned at a different point of time, they might get a different outcome, right?
That's true. Yeah, so fairness with respect to timing is interesting. One thing I will say is that, again, the way the algorithm works, there doesn't have to be like a fixed end time, and it'll simultaneously guarantee these multi-calibration guarantees, at every, prefix of time, but the bounds are worse for smaller prefixes. But somehow, inevitably, if you're learning, especially in an adversarial setting, but also in a distributional setting, there's no way to avoid the need to make different predictions for the same person if they come later, because if they come at step one, nothing about them, and so there's nothing you can do except make a bad prediction. And so you're learning over time by seeing the data, and the nature of learning is that you're going to realize that earlier predictions were maybe not the best ones.
I see. So this notion of temporal inconsistency and noise, as Kahneman these days keeps talking about, inconsistency over time, these sorts of, are there measures that people are looking at that?
Let's see. So there has been sort of some work on fairness over time. There's at least one paper I've seen along these lines, but you have to do funny things to deal with the fact that you don't know anything at the beginning, and learn more. And so the solutions are often okay, well, let's conservatively treat everyone terribly at the beginning so that we can only improve with time. And it's not obvious to me that, so there might be good ways to think about this. Yeah, it's an interesting problem. I haven't seen sort of a great way to think about fairness with time that sort of grapples with the fact that we're just going to have to make incorrect decisions a lot of the time before we've seen much data.
Thank you.
I'm afraid we have to stop now. So we are going to have a discussion table afterwards in 10 minutes. So I hope Aaron can stick also for the discussion table, and then we can continue questions and discussion there. Thank you, Aaron, again.
Thanks for having me.
10 minutes break.
Okay, so welcome back, everybody. I'm Massimiliano Pontil, and I co-organized this workshop together with Isabel and Evgeny. So in this last session, we are going to open the discussion to everybody. So the format is that everybody can ask or answer questions or make comments. We have a group of panelists who include the speakers and some additional people that we have invited. So I'm going to introduce them. We have Jean-Michel Loubès from the University of Toulouse, Paul Sabatier. Is a mathematical statistician working on algorithmic fairness. We have Nikki Kilbertus, so I hope to pronounce all the names correctly, but it's unlikely, from Helmholtz AI in Munich, and he's an expert on causality and fairness, and also has done some work on privacy. And then we have Krishna Gumati from the Max Planck Institute for Software Systems. He has done quite a bit of work on fairness, and he is an expert on social computing systems and like online social media. And finally, we have Julian Fierretz that was speaking before from the Universidad Autónoma de Madrid, and also he has work on fairness and biometrics. So the format is that everybody can ask questions. If you are muted, you can raise your hand and we unmute. And people on YouTube can also ask questions or make comments, and we will read the questions in order. So when you speak, turn on your camera. And so there are many point of views, as you have seen during the talks in this area. So people don't always agree. You can express your view, but please, very important, be always polite. So, so the focus of the workshop is on the foundations of algorithmic fairness from a machine learning perspective. So I want to start the discussion, today's discussion, asking one question, and then we can move on. So the question is, what are the next steps on the foundation of algorithmic fairness? Are we all set up, or what is missing, right? So to be more specific, do we have a good problem formulations for algorithmic fairness? And so one reason I ask this question is that if we have a good formulation, I think this is the way to perhaps attract more people working on the foundations of machine learning also in this area. So I think this would be very nice to let the field grow further. So so what is your view? Please speak up and let's start.
All right, I can speak up if no one else wants to. So I think the field is just beginning, you know, and there's still lots of interesting work to be done just on sort of basic, you know, like myopic definitions. What are the things that we're, you know, at the most basic level trying to accomplish? And a lot of my work is still thinking about definitions. But going forwards, you know, what we've become, at least for our sort of restricted set of definitions, pretty good at thinking about is sort of the myopic effects of imposing some, you know, little algorithmic tweak, you know, equalize false positive rates, or try something with subgroup fairness or individual fairness or something else. And what we are not so good at is thinking about how these sort of myopic algorithmic tweaks will sort of propagate to, you know, the larger, you know, socio-technical systems that are the things that we actually care about. You know, generally these algorithms are not acting in isolation, they're mediating human behavior. And there's like a little bit of work on this, I would say, in sort of two flavors. But like the first flavor says, if you don't know what is sort of the function mediating your choices today to what happens tomorrow, then there's nothing you can say. You know, like any constraint you can think of could be either good or bad. And the other flavor is to make very specific assumptions, to write down a model, maybe a game theoretic model, and then say very specific things. But of course, everything you say in a model like that is subject to the criticism that your model is oversimplified and is not capturing something about the real world. And I think a very interesting direction for the next few years is to try to think about relatively robust ways to actually make plausible predictions about sort of consequences of algorithmic tweaks, which I don't think we have right now.
So any other comments or views?
Yeah, I'm happy to talk next. I think is an interesting angle I'd definitely like to see more is sort of acknowledging the coexistence of fairness goals and requirements with other principles and requirements. So I briefly, during my talk today, I mentioned trade-offs between fairness and data minimization, but there are other aspects. So there's, for example, user agency that I think are underappreciated. So sort of seeing more work about fairness in context would be great. And related to that is I work a lot on human factors, and very often the way we think about human factors is sort of like an after step. So we model fairness first, and then we look at how these models are deployed in practice and how users interact with the solutions. I think it's also possible to start from the other one. So formally model the human factors and incorporate them into the formal definitions. So I would think that this is a great direction as well.
I'm sorry for joining a little late. Apologies. Can I know the question again?
The question is, what are the next steps on the foundation of algorithmic fairness? Are we all set, or what is missing? Or what are good problem formulations?
I see. Thank you. So am I one of the next people? Okay, so sorry for missing the first few minutes.
Anybody can speak.
Okay,
yeah,
yes.
Please.
So I think from my talking about some of the things that we are doing within my group, so a lot of the focus on algorithmic fairness has been on tasks that involve predictive analytics kind of applications, right? And I think increasingly there are algorithms that are being used in the context of markets and doing matching. Like, for example, if you think of market making algorithms or matchmaking algorithms that are used on sites like Uber or Airbnb or these DoorDash kind of delivery services, or and so on, you have essentially different types of stakeholders. You have, for example, if you think of DoorDash or any of these delivery restaurant delivery apps, you have one set of stakeholders are the restaurants, another set of stakeholders are the people who are delivering the food to homes, and the other set of stakeholders are customers, right? And oftentimes in these marketplace algorithms, if you're thinking of fairness, it actually becomes more nuanced and more complicated, because you have issues related to being fair amongst the restaurants on one set of stakeholders, and being fair to the delivery people, another set of stakeholders, or another set. There are multiple different stakeholders. And now you have to deal with issues related to performance versus fairness trade-offs across different sets of stakeholders. This makes the problem more richer and also more interesting to think about, compared to predictive analytics situations where often there is one set of stakeholders and you're trying to be fair amongst them, and you have notions of individual and group fairness to address those kinds of scenarios.
Okay, I'll add maybe one problem I've been considering next. So I feel like it's not even so like well defined, and I haven't seen a lot of work on this topic, is a fair data collection, because we always talk how the data we have causes biases. And I mean, we have a lot of data and we want to use it, of course, but maybe going forward, we want to also introduce some techniques that help us collect the data such that in the future, because I mean, even though we develop all these fairness techniques, when people deploy products, they don't always use them because sometimes they're computationally harder or they just need to know more to use them. And so if the data can be itself like somewhat debiased, then the people who are developing products, they can just throw their favorite deep learning algorithm on top of it and get something out of it that wouldn't be discriminative. But even what does it mean for data to be fair? It's not so clear to me. So I've been thinking about this problem for some time, but it's, I don't think it's very well defined. So I think it's an interesting also problem to look into.
So you are thinking of a more interactive approach to, a lot of work on fairness assumes that the data is given, so it's maybe passive, so, but you are thinking of something more interactive. And but how will you go down this direction a bit more? Do you have some ideas?
For instance, I know that sometimes people, like in companies, they collect like crowdsourced data collection. So they pay people to go take photos of things on the streets of like certain types of things. Let's say we want to do like a text recognition from images, so we can ask people to go take photos of street signs and stuff like that. But instead we could tell them, well, we'll pay you more if you give me like a red text on a blue background or something like that. Like if you give me a picture of a blue bus with some commercial in it, rather than arbitrary bus. Something like that. But the goal here is reversed. So once the data, so the idea is that we want a procedure to collect the data. So yes, so the algorithm will come at the data collection process, and it should probably incentivize certain types of data rather than arbitrary data. And then what we want to achieve, I mean, again, it's not very clear and it's up to debate for sure, but what we want to achieve possibly is that now if we do like simple empirical risk minimization on top of this data that we've collected, then suddenly whatever comes out, let's say, satisfies group fairness right away without us trying.
Okay. So
in addition, if I could contribute, I did review the schedule of the whole workshop, and it would be an interesting topic, which also is quite complicated. One is the recursive effect of fairness application or data collection minimization. So basically, if you have a setup when you apply a model and you apply predictions, these affects your surroundings, and you collect the data back from populations which are affected by your predictions. That creates sort of second order impact on all ecosystem. It would be interesting to see if there is a research that could address that question, which I'm pretty sure it's quite complex one.
I'd like to follow up on what Aaron said and would also be interested in your opinion here. I also find it interesting to think beyond sort of the myopic criteria we had so far and see sort of how these data-driven systems and humans sort of interact in societal applications. And I guess one approach to this is from a game theoretic perspective, mechanism design, sort of viewing them as different actors in a larger environment that interact. And what I'm curious about is to what extent this model captures discrimination that we worry about, in the sense of that this seems to be almost an emergent phenomenon to some extent out of society interacting at large. And I'm not sure to what extent it's captured in sort of making this model of individual agents of sort of machines and humans, and they interact in some ways, and to what extent it's just a property of the entire system. I don't have any good ideas in this area, but I would be curious what people have to say to this.
Yeah, I mean, it's a good question. So there's a long economics literature dating back to the 70s in which people write down game theoretic models, and you can recover, self-fulfilling prophecies of discrimination. So the original models were of the sort everyone's equal when you're born, but you can basically decide to study hard or not, and employers want to hire people who study hard, and you can't directly observe that. And it's a symmetric game, but there's equilibria in which group A studies hard and employers hire them, and group B doesn't study hard and employers don't hire them. And this is a equilibrium. It's rational for everybody, because if you're in group B, why would you study hard? You're not going to get hired. If you're the employer, why would you hire people from group B? And right, so you can recover things, and these models are fine as far as they go, but obviously these are toy models that don't capture all sorts of things. So to sort of point to the obvious one, in the classic models, not everyone has the same access to education or other kinds of opportunities. And so you can write models that capture, you can write down models that capture that stuff as well. And in fact, I spend some of my time doing that. I sort of like the game theoretic approach. But I think in general, this agenda is always subject to the criticism that you can find, in your model, you can derive findings, but okay, now it's time to translate those findings to the real world. What has it really taught you? And what you ideally would like to be able to argue is that the findings are sort of robust to all sorts of perturbations of the model, that it wasn't specific to, the arbitrary choices you made in the model. But that's of course hard to do. But let me say that among approaches to thinking about the long-term effects of sort of algorithmic interventions, I think game theory is sort of the most promising one, in that, if you are not willing to assume anything about how the future connects to the past, then, you run into sort of obvious impossibility results that anything you do could be good or bad. If you take a sort of much more general, reinforcement learning methodology, okay, in principle we can solve reinforcement learning problems, but in any actual problem we care about, we don't have the number of iterations to actually run a reinforcement learning algorithm to convergence. And so I would say the game theory approach is for sure problematic, but I would say it's maybe the least problematic of the ones I've seen.
So I guess, are there ideas or approaches in this game theoretic perspective? It sort of seems to assume that people take individual actions or maximize some individual utility and be strategic in some sense, do optimal move. To what extent can we capture phenomena like in-group versus out-group, or us versus them thinking, which seems to cause a lot of the discrimination or unequal access that we see in practice? Those don't seem to be driven by any sort of utility, by any economic strategic thinking. This is more like, which football team do I happen to like? And that already, causes these discrepancies.
I think you're underselling the creativity of game theorists. So, for example, why to, and I'm going to give silly examples because, again, any toy model is subject to criticism of the brittleness of the model. But for example, suppose you want to explain why Chinese restaurants tend to hire Chinese employees. Okay, so this is sort of an example of the in-group versus out-group thing maybe you're talking about. Well, you can say, okay, well, different population, maybe everyone is sort of equal in distribution over talent. So there's people who are going to be good restaurant employees, there's people who are going to be bad ones, but there's different mappings between observable features, when you're interviewing someone and how good they are. And if you happen to run a Chinese restaurant and you live in Chinatown, then you have lots of experience learning the mapping between good employees and bad employees within your population. But you're mapping for other populations, you just haven't had the data to learn it. And so you can write down a model like this in which, it is an equilibrium that people hire employees like themselves, again, without sort of baking in taste for discrimination. Now, what you learn from a toy model like this is up for debate. But I would say that game theory is an expressive enough language to capture all sorts of phenomena.
Nice. Yeah, I think that's what I was asking. So that just shows my ignorance of the creativity of game theorists. But that's cool. Thanks.
So any other questions? Or comments?
I want to build up on one of the earlier discussions about the sort of increased data collection for improving bias and the sort of interactive data collection. Interestingly, in GDPR, there's this requirement of adequacy, that is, people sort of have the right to have their image adequately represented on the service provider side. And that sometimes might mean that the service provider should actually collect more data about the user, so that the user at least should have the option to provide the service with the data they think the service lacks. And I think we currently don't have mechanisms for doing this, and it would be interesting to see what effects that has. So that's a comment I had on one of the earlier discussions. I do have a question about game theoretic approaches as a follow-up on the recent discussion. And I'm curious to what extent are these toy models applicable in the real world? Because I mean, in practice, you have lots of factors influencing people's behavior. So I'm wondering if there are any scenarios where you can actually take these toy models and apply them and get good predictions or results.
Yeah, so I would say at best, what you might hope to get from a toy model is sort of like a distillation of a rule of thumb that you could apply to the real world. Not that you would sort of compute like numerically, like, you know, this is the equilibrium strategy, but you would sort of distill some phenomena. So just to give an example, you know, suppose you're suppose you've gone back to 2016 and you've just read the ProPublica article and you're thinking, you know, like in criminal recidivism settings, should I equalize false positive rates or false negative rates across groups? Should I equal positive predictive value? You know, we know you can't do it all. You can write down a game theoretic model that sort of says, okay, well, you know, maybe there's different populations that have different access to legal opportunities. Maybe everyone, you know, has some sort of legal opportunity that's sampled from some distribution, but it's different for different populations. And then everyone's going to make like rational decisions about whether to commit crime or not as a function of the incentives engendered by, you know, the criminal justice system. And you can write down models for which you actually sort of derive that if you want to minimize crime rates, the thing you want to do is equalize false positive rates and false negative rates, even though that is not myopically the sort of you know, best predictor of crime. And the reason, and maybe this is like, you know, the thing you extract from such a result, not the like not the sort of details of the model, but the reason is because if you do the statistically optimal thing to predict, you know, criminality, which, like, you know, the Bayes optimal predictor will engage in racial profiling, because if there are different base rates across different populations, you know, that's like statistically informative. But the reason you don't want to do that is because if I condition on your demographic group, which is sort of what I need to do if I want to have sort of equal positive predictive value, then people from the group that have the higher base rate of crime are subject to a sort of lower threshold of evidence to punish them. And this distorts their incentives. This makes crime sort of relatively more attractive, because if people are already predisposed to judge you negatively because your demographic group has high risk properties, well, that like reduces your disincentive to you know, prove them wrong. And so sort of maybe one thing you can take away from such a thing is that if what you want to do is, you know, minimize crime rates, for example, maybe what you should be focusing on is providing everyone with the same disincentive to commit crimes at an individual level, since that's what matters, and realize that that is sort of incomparable or incompatible with doing statistical inference based on features that are properties of their group that they cannot influence themselves. So rules of thumb, I think.
I wanted to follow up on Asha's earlier comment as well regarding this connection between data minimization, fairness, and accuracy. So I think there was this recent work by John Kleinberg as well, but maybe just to talk about it a little. So sometimes collecting more data from certain groups can help you make a more informed decision, right? Say you're hiring for college admissions, and then you just look at the resume, you don't know enough, perhaps for students from good colleges and large number of publications or something, you can make the decision much easily, whereas perhaps from students who are from like minority groups or from countries that are not as popular and so on. So maybe there you need a little bit more information. Perhaps you want to collect a little bit more data. So here, more data is helping you make a more accurate prediction and perhaps helping in fairness in certain regard, but it is has this conflict with the data minimization principle, right? So I just wanted to ask in general, like what do people think regarding selectively asking more data from certain people, and also in general the trade-off between certain GDPR principles like data minimization versus fairness and accuracy?
So I think, if I can, I think this is a great question. In fact, there are these legislations called ban the box in the US, where employers or prospective employers are sometimes prohibited from asking certain information about prior, say, criminal records of people, and banning them because it's meant to improve it's meant to help potentially avoid certain types of discriminative behaviors and so on. But every time you prevent, but the effects of that legislation has been debated quite a bit, because sometimes when you're prevented from obtaining certain amount of information, the question is, would people start making assumptions about it? Because now with less information, would you start generalizing more about what somebody's qualifications might be if you had no information beyond a specific set of things? So I do think this raises a whole bunch of interesting questions when you in terms of you can talk about, I think you can talk about when you're making judgments, should you be using the same amount of information for everyone, right? So oftentimes in many standard machine learning models, we take this for granted. We assume that we have the same features for everyone. But what if there are scenarios where where you don't have all the same information for everyone? In fact, when people push for structured interviews, or when we set exam papers for all the students, we give them the exact same questions. I mean, you could ask what would happen if you asked very different questions, and then could you still compare their performances or whatever, right? So there are a whole bunch of scenarios where one could argue that you should, when you're making judgments, to be fair, maybe procedurally fair, you should have the same exact input data for everyone. But then on the other hand, that runs into conflict with, what if you don't need as much data for some people to make the same decision, and you need more data for others to make decisions with the same confidence or whatever? This is the data minimization principle that Asha was talking about as well, right? So there are interesting trade-offs between these different things, like data minimization versus accuracy and fairness in terms of how much data you're using for different people. We did explore one operationalization of this, of these three things, and then you'll end up with some sort of impossibility results saying that you cannot achieve all of them at the same time, and you might have to give up one over another. But it all depends on how you're operationalizing these sorts of things. But there are some very interesting, tricky questions that come up once you start allowing for the fact that you might be using different amounts of data from different people to make predictions. And especially if that is in the hands of the people who are providing the data, then you have a whole bunch of other interesting strategic strategic classification kind of questions that come up. Like, would someone strategically choose to reveal some information about them and not reveal other information about them because they know that now if they revealed a different data, different features, and didn't reveal some features, they might get a better outcome than they would have gotten. So there's a whole bunch of interesting things to explore there, I think.
Yeah, actually, all these questions raise quite interesting speculation on my side. For example, as criminality prediction that Aaron mentioned. In that case, it looks to me that's probably some models need to be inverted. Basically, try to predict the causes of criminality and address them in practice.
So we have 10 more minutes.
Let me also add my 2 cents to the discussion, to the open question that you raised, Massimiliano. Are we missing something for a good foundation of researching fairness and fairness technologies in AI? From my point of view, among other things, like having more data and good data for researching fairness, like Misha said before, labeled perhaps to some extent. We need more definitions. So we need definitions of the different elements in fairness. So like, for example, group fairness, individual fairness, and together with those definitions, we need also to explore variants. There is no a single way to define, for example, group fairness. So we can have fairness between groups, and within one group we may have individual fairness. So there are different variations, and for those variations that may work differently in different problems or applications, then we may adjust some variables, some parameters. So I don't expect to have like only one formulation or one single formula to work the fairness in artificial intelligence system. I see fairness like a toolbox that depending on the application elements, groups involved, features, you may have to use different tools. So and there is no a comprehensive I would say taxonomy of the different tools that we have now. So we have many different disciplines stating what is fairness, how you define it, and then how you operate or how you optimize your fairness. So for me, we have now in the state of the art is kind of different elements that we need to have to put them in order somehow, and then perhaps experiment with different variants in different applications, and perhaps find like one I don't know, a killer application or a distinctive application that may attract audiences beyond the core research in artificial intelligence, and then that we can convey a good message with that. So many different still missing points in my opinion, and good research lines are open here in fairness in artificial intelligence.
Maybe just to add a little to these various definitions, I wanted to say that I think there is very little work on assumptions that these definitions make. And I think this needs to come a lot on the forefront. For example, a lot of these group fairness definitions, which depend on, let's say, equalizing error rates or something. The implicit assumption over there is that the target labels in your data set are correct, or they're not biased, but this is hardly ever the case, right? For example, when you're using arrest information to predict crime, then there's naturally a bias in this target label. So and there are similarly for various other, like, for example, for individual fairness, when you say similar individuals should receive similar outcomes or something. So what is similar? Does it have to be similar in the observed feature space in the data set? Or is it similar where you need to actually elicit some kind of similarity, right? I think there was work from Aaron Roth and also from me and others in this regard that maybe what is the current data set has certain societal bias, which cannot be addressed just by training more and more models on that, on top of that, right? So you need to, you need some form of mitigation strategies to actually combat this bias that is embedded in the data. Sort of that the features that are collected are not sufficient. There is, for the decision making, there's a lot of other features that are not embedded there, and you need to sort of model this information in some regard. So maybe all this to say that there are a lot of assumptions that are made when you talk about various fairness notions and operationalization approaches. And would be nice if all the works also came along with what are the assumptions that they are making, right? Some form of a discussion at the end of the paper, like where does this really fit in this entire space? What kinds of biases can it really address and not?
Yeah, I think that's a great question. And let me highlight, there was a nice paper at Fork last year by Avram Blum and Kevin Strangle that is sort of, you know, I think is getting at an important area that I hope, you know, other people follow up on. So when you think about the fact that the data that you collect is biased, you know, okay, like you want fairness with respect to some, you know, like a ground truth, which you don't have access to, how are you going to do it? Well, you know, okay, if you sort of know the mapping between ground truth and the observed data, then you can sort of try to invert it, but you know that's never going to be the case. And what Avram and Kevin are able to show is an instance of a kind of result that I think is powerful, which is sort of a detail-free result. They describe a whole family of mappings between you know, sort of ground truth and collected data. So these can be, they consider different kinds of data bias, both that you might just collect less data about positive examples from a minority population, or maybe that the labels would actually be flipped. And they show that in sort of a parametric family of sort of data bias models, simple ERM procedures that, for example, you know, attempt to sort of equalize false positive rates on the observed data can sort of recover from the data bias. And the nice thing here is that it's like a detail-free result. Like you don't need to know the actual parameters of the bias model, which you can never know. It sort of says, you know, here's some general, you know, reasonably expressive collection of bias models, and simultaneously for all of them, without knowing the details, here's a simple algorithm that can sort of obtain, you know, classifiers that are fair with respect to the, you know, unobservable ground truth. And, you know, that their particular paper, it's the first paper, it's got various like limitations and such, but I think that this is a very nice style of result, like a detail-free algorithm that can, without knowing the, you know, fiddly parameters of sort of this unknowable model for how, you know, ground truth is mapped to collected data, can correct for it even, you know, under suitable assumptions.
Maybe to very briefly connect to this, I think the nice thing about this formulation is that we're definitely not the only community thinking about these things, right? So there is definitely then a lot of connection and overlap to people thinking about domain shift and what are the domain assumptions or the shift assumptions, and what is a reasonable family of shifts that may occur in practice. And you know, this ties into a lot of other communities where I think there could be fruitful collaboration and overlap in finding what are the real things that happen at test time that we didn't see at training time. I think this is one of the overarching questions. And I agree that trying to formulate a characteristic set of things that could happen, as Aaron just said, that seems to be one fruitful way forward.
There are also some connections to information retrieval where people have developed techniques for debiasing collection of ground truth for relevance. So in ranking systems, you collect implicit relevance from the way people interact with the rankings, like how they click, what results they inspect. And of course, this is prone to a lot of cognitive biases people have. For example, they tend to pay more attention to the top ranking positions, right? The position bias and other types of biases. So there are techniques for debiasing this relevance information. I guess it would be interesting to see whether those techniques would convert to other setups of classification.
If I can make it just a quick comment, I'm a little surprised nobody brought up causality and causal reasoning into fairness, and particularly Nikki. Is it that I was just wondering if that is because it's proving to be, I mean, in general, reasoning about causality is very difficult, or?
I was about to bring up causality. Actually, I was looking for Ricardo, but I'm not sure he's there. We are a bit over time, so maybe we can either continue the discussion next Tuesday, or maybe let's take maybe 4 more minutes if you agree, or to discuss discuss causality. But we might need more time.
Yeah, I guess probably best to give this a bit more time next time. But maybe to just briefly talk towards Krishna's question. I do think so far what we've seen, the idea of causality mostly relied on thinking about causal effects of things that are race, gender, social constructs. And I am a bit concerned about whether we know how to actually capture these concepts and what it means to put them in a causal graph. So there's many people thinking long and hard about this. Isakola, Hausmann, Lily Hu, and many others. And yeah, these are definitely things that I worry about when trying to use causal modeling to make claims about fairness and unfair influences, causal influences in society. And this connects, I think, to what we discussed before in terms of these being sort of properties that come out of interactions of people, not, or more, properties that come out of the interaction rather than just set in stone properties of people that have actual causal influences. So I do think there's value in thinking about cause and effect in the sense of what are the drivers of these phenomena, what causes sort of the discriminatory aspects that arise in society. I'm not sure we are completely on the right track with thinking about the actual causal influence of race or gender and how that is fair or unfair. But yeah, I think there's a lot of nuance to that, so definitely worth giving it more time.
Yeah, maybe very briefly, I'd say causality is obviously a very attractive way to think about these problems in principle, but I think that the same kinds of criticisms you can level at individual fairness or sort of game theoretic models can be leveled at sort of the causal fairness literature, but maybe even more so, which is that if you buy the causal model for the world, then you get some sort of crisp results, but your model is always wrong. It's always a simplification. And the question is, how brittle are the takeaways to the particular modeling assumptions? And I think sometimes they can be quite brittle. And so, the causal fairness literature seems to me to be sort of a promising long-term way forwards, maybe, like a research agenda. But I think this brittleness sort of makes it hard to imagine making it actionable in, any kind of short-term future.
And I think we are in causality, we are paying a lot of attention and trying to improve our sort of sensitivity analysis, getting a better feeling for how brittle our sort of world models are. But we're definitely far behind what people have done in other fields like game theory, like other approaches where we have a better understanding of how brittle these systems are, how easily they can be fooled and gamed. And the idea of sort of putting bounds on causal effects and understanding how sensitive our results are to the underlying assumptions and this causal model of the world, there's still a very long way to go.
Okay, so maybe we can continue next Tuesday. So we start at the same time, 2 p.m. CET. So thanks very much. Thanks to the speakers and thanks to the people who joined the panel. So see you soon.